Okay, so welcome to the first lecture on the vectors course. This is the basics, vectors versus scalars, vector notation, addition and scaling, and properties. Alright, so begin at the beginning. Let's list some scalar quantities. Think about mass, duration, length, temperature, charge. These physical quantities are all well described with a single number. Really, they just have a magnitude, although some of them may go negative, so it's a magnitude and a sign. But still, just a simple number is adequate to describe these things. How about vector quantities? What's different about vector quantities? Well, think about these things: force, velocity, and therefore acceleration, or momentum. These things also have a strength or a magnitude. However, so let's put that down. They have a magnitude. However, they also have a direction. More than just a sign, they have a full-on direction in three-dimensional space. So it's not enough to know that a force is 3 newtons. I want to know in which direction is that force applied. And that then is the difference between a vector and a scalar quantity. We're going to think about how we manipulate them. Alright, so first off, the notation that we're going to use when we talk about our vectors. What I'm going to do is I'm going to use a symbol such as the letter A. So let's write that out, but I'm going to underline it. So an underlined symbol indicates a vector rather than a simple number. And when I need to specify that vector, I'm going to write it, so it's going to be three-dimensional. I'm going to write the 3 numbers in a column form like this. Now, if you haven't seen a vector specified before, what does it mean? Well, think of the Cartesian axes, the x, y, z axes. Think in this case about coming out from the origin 2 in the direction of x, and 1 in the direction of y, and 3 in the direction of z. What we're going to do is we're going to think of our vector as an arrow that comes from the origin to this point in space. And that arrow itself, whether or not it comes from the origin, that direction and that length of arrow is our visualization of the vector. So let me just change color to green and go ahead and draw the tip of my arrow there. There we are. So the vector is coming towards us out of the screen, and it has those particular 3 components, 2, 1, 3. Other people may use other notations. For example, a line over the symbol A is commonly used. When people write out the components, they may choose to do it as a row like this, or even using pointy brackets like this. Now, all these notations are basically getting at the same thing. You'll be able to read textbooks or look online and see these things and understand what they mean. But within this course of videos, we're just going to use the notation that I've introduced above, so I'll erase those for now. Now, the simplest thing that you might want to do if you have a couple of vectors is to add them up. So let's think about that. Vector addition, what does it mean? So let's give ourselves a second vector b. We'll make it 5 minus 2, 0, let's say. I want to add these 2 vectors together. So we'll write that out. I simply want to add a underline plus b underline. What does that mean? Let's just substitute in 2, 1, 3. Add it on 2, 5 minus 2, 0. Now what we do is we simply add the first component of vector A to the first component of vector B, and so on down the list. Very, very simple. So we're adding 2 plus 5. We're going to add 1 plus minus 2 and 3 plus 0. And we just tidy that up. So that's going to be 7 minus 1 and 3. Now, how about scaling a vector? Okay, so what we can do is we can multiply a vector by a simple number, and correspondingly we'll just end up multiplying each of its components. So let's take an example: 3, 9 minus 12. What we notice is each of the 3 components is a multiple of 3. We can just take that common factor out in front and write this instead as 3 times 1, 3 minus 4. Same thing. Alright, or equivalently, someone might give us a vector that's already written in this form. Could be, let's say, 3 over 2 onto 2, 4 minus 4, let's make it 1. Alright, and we can just multiply that in a component by component basis. So we just write ourselves a new column. Of course, 3 times 2 is 3. 3 times minus 4 is minus 6, and 3 over 2 times 1 is 3 over 2. Okay, so there we are. We can scale our vectors by a number in this simple way. So with these definitions of addition and scaling, can we say anything about the properties? Okay, so if I have two regular numbers a and b, then of course a plus b is the same as b plus a. I'm not saying anything fancy here. It's as simple as, I don't know, 7 plus minus 3 is equal to minus 3 plus 7. Obviously it is, we know that. Now, if we think about the same statement for vectors, a plus b, vector b, is it the same as vector b plus a? Well, it must be. Let's just write out an example. 7, 0, minus 1, 3, 1, 2. Is it equal to 3, 1, 2 vector plus the vector 7, 0, come on, 7, 0, minus 1? Of course it is, because of the way we've defined vector addition as just being the addition of each element to the corresponding element. And this property is called being commutative. Okay, so vector addition is commutative. How about this second example? If we have three basic quantities, ordinary numbers, then if we have a plus b plus c, it's the same as a plus b plus c. It doesn't matter the order that we do them in. Is that going to be true for vectors? Well, of course, it is going to have to be true to vectors, because the way we define vector addition is to add each component to the corresponding component. It's just addition. So this is also for vectors. And let's write out what we mean. We mean that vector a plus b plus c as a previously worked out thing is equal to vector a plus vector b and then add on c. It doesn't matter the order we do these things. Alright, and there's a name for that property. It's called being associative. Associative. Alright, so vector addition has that property also. Now let's think about our scaling property. If we have ordinary numbers again, then we could take some scale factor k and multiply it into a plus b, and it would just give us k times a plus k times b. Again, I'm not saying anything that isn't utterly obvious here. Say, for example, I don't know, 2 into 1 plus minus 3 is equal to 2 times 1 plus 2 times minus 3. Of course it is. So how about for vectors? Is it true that some scale factor k times the sum vector a plus vector b, a plus b, and let's stress that this scale factor is just a pure number? Then, yes indeed, it's going to be just k times a plus k times b. So just to stress what we're doing here, let's copy down this sum of two vectors we were playing with up here, this 7, 0, minus 1 thing, plus 3, 1, 2, put it inside curly brackets maybe for a variety, doesn't have to be curly brackets, multiply it by some factor. Let's have 3 over 2, had that before, unimaginative, there we are. What's that going to be? It's just going to be 3 over 2 times the first vector, 7, 0, 1, and then plus 3 over 2 times the second vector, 3, 1, 2. Okay, so everything as you kind of would expect it works out. It must. And this latter property is called being distributive, excuse me. So scaling is distributive over addition. And that's the end of our first video. Welcome to the second of these videos. We're going to look here at the vector dot product, also called the scalar product. We'll look at also the magnitude of a vector and the meaning of unit vectors, the geometric meaning of the dot product, and finding the angle between vectors using the dot product. Okay, so the dot product is a way of combining two vectors in order to produce a number, a simple number, a scalar, hence the alternate name scalar product. Let's give ourselves a couple of vectors. Let's have a, well, vector a can be 4, minus 4, let's have 2, 1. And we'll have a vector b, which can be 3, 1, 3. And we're going to do the dot product of these two guys. So we write that as vector a nice clear central dot, vector b, and then we write that out as the two column vectors, and we need to understand how we compute the dot product. And the answer is we're simply going to multiply each component by its opposite number and then add them up. So we're going to multiply the first component, minus 4, by 3, and then add that to the second component 2 multiplied by its opposite number 1, and finally the third components 1 and 3. So that's minus 4 times by 3 added on to 2 times by 1 added on to 1 times by 3. So minus 12 plus 2 plus 3, that's going to be minus 7. Alright, there's the dot product worked out. Pretty straightforward. And of course, as you can see, it can be a minus number. It can be 0, it can be a positive number. But it's a simple, pure number. Okay, so now let's see what happens if we do the dot product of a vector with itself. Let's do A dotted with itself. So that's going to be minus 4, 2, 1 dotted with minus 4, 2, 1. Now, of course, because we're multiplying each component by itself, that will always be a positive number. 16, minus 4 by minus 4, and 2 2s are 4, and 1 1 is 1. And so that's going to add up to 21. It must add up to a positive number. It's made of 3 positive numbers summed. Now, I want to introduce a second vector called A hat. It's related to A just by scaling it. And we're going to scale it by 1 over the square root of the earlier dot product with itself. So 1 over square root 21. And then just minus 4, 2, 1 as before. So that's just a scaled version of A. What's interesting about it? Well, now let's see what happens if we take the dot product of A hat with A hat, with itself. So we're going to get 1 over square root of 21 times 1 over square root of 21, which is 1 over 21. And then, of course, we're going to get A dotted with A, the original dot product we did, which is just 21, as we know. So, of course, the dot product of A hat with itself is just 1. That means that A hat has a special property. It's what's called a unit vector. Unity being, of course, a fancy word for the number 1. So when we scale a vector so that when dotted with itself it comes out as 1, then it is a unit vector. Meanwhile, in general for a vector, the square root of the dot product with itself has the name magnitude. This is the magnitude of a vector, and it is also magnitude. It is also the length of the arrow if we think in terms of a vector as a physical displacement, an arrow that lives in three-dimensional space. Then it would be the length of that arrow, as you can see from Pythagoras. Okay, now then, a different thing. The dot product between two vectors has an alternative definition, which we can show is the same as the definition we've been using so far. A dot B is also the magnitude of A times the magnitude of B times cos of some angle. And what is that angle? It's actually just the angle between the two vectors, between their directions. So here I'm drawing a vector A going in one direction and almost in the opposite direction vector B. And then the angle in question would be this angle that we see between the two vectors when we draw them coming from a common point of origin. Okay, so it's important to understand then that this angle can be more than 90 degrees. Here's what it isn't. Here's a mistake that's sometimes made by people as they start to play with vectors. They want the angle, for some reason they want it to be less than 90 degrees, so they try and contrive this by putting the vectors together in a way that will give them less than 90 degrees. Like this, for example, and then we could try and draw an angle between these two lines. Let's see, let's use a red to show that it's not correct. What we should have is the two vectors coming from a common origin. Then we see that the angle between them can be more or less than 90 degrees. If it was exactly 90 degrees, then of course the dot product would be 0, because cos of 90 is 0. That has interesting consequences. But right now let's work out the angle between a couple of vectors. Let's give ourselves A, we'll make it 1, 0, minus 1, and B, we're going to make it 4, 1, minus 1. And we'll do the dot product between those guys. So first we'll work out the dot product. Actually, let's make it minus 1. So A can be minus 1, 0, minus 1. I think that will come out better. So we have minus 4 from minus 1 times 4. We have 0 times 1 is 0. And we have minus 1 times minus 1 is 1. So it's going to be minus 3 for the total dot product between these two guys. But we also need to find out the magnitude. Fair enough. Magnitude of A is going to be the square root of minus 1 times 1 is 1. And again, 1. So that would be the square root of 2. Nice and straightforward. Meanwhile, the magnitude of B is going to be 4 4s are 16 plus 1 plus 1. It's going to be 18, the square root of 18. but I think we can do better than that. Square root of 18 is actually square root of 9 times the square root of 2, and that means it's 3 times the square root of 2. Okay, now we've got everything we need. Let's pull down a copy of that definition there, relating a dot b to its magnitudes and the angle, and fill in what we know for this particular choice of a and b. We've got minus 3 is therefore equal to root 2 times 3 root 2 times cos of the angle that we're after. So now we just need to rearrange. That means that cos of the angle is going to be equal to minus 3 divided by, well, we've got two lots of root 2, so that's just going to be 3 times 2, and if we simplify that down, it's just going to be minus a half. Now we may just remember, or else use a calculator to find out. This means that the angle in question is in fact going to be simply 120 degrees, or you can use radians if you prefer radians. So there we are, that's the answer. The angle between these two vectors, 120 degrees. And that's it for the second video. In this video we're going to see how to calculate something called the cross product of two vectors. It's also called the vector product because the output is a new vector, and we'll see how to test that the answer is correct. So here I've written A cross B is equal to C, and notice that the symbol for the cross product is just the multiplication symbol that you're familiar with from basic arithmetic. I've given the vector A a particular form, this 2, 3, 4 column vector, and similarly B is written as 4, 5, 6. So we're going to go ahead and find out what is the cross product of these two vectors C. Because it's a vector, we'll need to do some working for each of the three components. Now what I'm going to do is I'm going to paste up some structure to help us work through the problem. So don't worry, because it's going to look like a lot, but you don't need to write all this out every time you want to do a cross product. I'm just putting it here so we can really spell out the process. Okay, so let's go ahead and work out the first component of the output vector C. Strangely enough, what we're going to do is we're going to ignore the first component of vectors A and B. So I'm just going to cross those out. Those aren't used. And what we're going to do is we're going to multiply certain of the other components. What we're going to do is we're going to multiply the second component of vector A with the third component of vector B. I call that the falling diagonal, because when we draw it like this, we start high and then go low. And then we're going to subtract off the multiple of the rising diagonal, 4 and 6 here, the last component of vector A and the middle component of vector B. So what we have here is 21, that's 7 3s are 21, minus 6 4s are 24, that's minus 3. We can go ahead now and write that in as our first element, minus 3. Now let's move to the second element of the output vector C. We'll start by ignoring the second component of the two source vectors A and B. We can cross those off. And again, we're going to multiply some diagonals. But what's different here is we start with the rising diagonal, 4 times 5. The last component of vector A times the first component of vector B, the rising diagonal. 5 4s are 20. And then we subtract off the falling diagonal, so 2 7s are 14, and that's going to give us 6. So we can put that in. Now let's move to the third and final component. As before, we start by noting that we will ignore the third component of the two source vectors, and we're going to need some diagonals. It's the same pattern as the first, falling diagonal first, so 2 times 6, and subtract, which is 12, and then subtract off the rising diagonal, 5 3s are 15. Alright, so that's going to be minus 3. Pop that in. We see that we have quite a simple vector here. There's a common factor of 3. Let's bring that out. 3, then minus 1, 2, minus 1. That is our vector C. That is A cross B. Notice again the pattern. It was the falling diagonal minus the rising diagonal for the first component, and then the rising diagonal minus the falling diagonal for the second component, and then for the third it was back to the same pattern as for the first. Now these look a bit like letters to me. They look a bit like a V, the middle one perhaps an N, and the final one a V. I like to remember that as a little sentence, which is vols never vary. Because in my opinion, vols don't vary very much. Here's a vol. This one doesn't vary at all because it's stuffed in a museum. However, if you compare it to some other vols, which I found these on the internet, I think they're all pretty much identical. I don't see a big difference there, so for me, vols never vary. If for you, they do seem to vary, then think of a different way of remembering it. But the important thing is that the first thing is the falling diagonal, and then subtract the rising diagonal, a V shape, and it alternates. Okay, how to check your cross product has been worked out correctly. This is really useful stuff. So let's give ourselves another example. We'll have 2, 3, 1, and then we'll have, let's say, 3, 7, minus 1. Let's get a minus in there. And that's going to be equal to something. We'll work it out in a minute. For now, I'll put x, y, z. Now, how am I going to test, once I've found those x, y, and z, that I haven't made some kind of slip? I mean, there's a lot of mental arithmetic. If we don't write it all out, we're going to be doing a bunch of multiplications. I could easily slip up. How am I going to test that? It turns out there's a very interesting property of the vector c that we get out after the operation if we've done it correctly. That is, as I've written here, that a dot product with vector c is 0, and so is b. So either of the input vectors a and b dotted with the correct cross product c should give us 0. And that's great because the dot product is very easy to work out even by eye as a check. Let's go ahead and do it. So I've copied it down here. We're going to want to work down our various components. Let's do the first component of C. So what do? We ignore the first components of A and B, and we do the falling diagonal. So that's going to be 3 times minus 1, and we subtract the rising diagonal, 1 times 7. So actually, let's just write that out. Normally, I wouldn't bother to write all this out, but let's go ahead and do it here. So it's minus 3 minus 7, and so that's going to be minus 10 as our first component. Now we work out the second component. We ignore the second component on the input vectors. We do the rising diagonal, 1 times 3, and subtract the falling diagonal, 2 times minus 1. So what have we got? We've got 3 here minus 2, and so that's going to give us 5. And then finally the third component, ignore the third component of the input vectors, do the falling diagonal, 2 times 7, 7 2s are 14, subtract the rising diagonal, 3 3s are 9. So we're going to have, for our final component, 14 minus 9, which is another 5. Aha! So that's quite a simple vector, has a common factor of 5 in there, if we wanted to write it out that way. Now let's test that guy versus the A and B vectors to see if it passes our test, or have we made a slip. So let's just be completely explicit about that. We're going to start by testing the dot product of the vector A with our hopefully correct cross product C. I'll write it out, 2, 3, 1, dot product, minus 10, 5, 5. What's that going to be equal to? Minus 20, and then 3 5s are 15, and then 1 5 is 5. Aha! It does equal 0. That's correct. That's a very, very encouraging thing, but for real thoroughness, we're going to test the other one as well. So this is B dot C. Let's check that out. So that's 3, 7, minus 1, dotted with, again, minus 10, 5, 5. This time it's going to be minus 30 from 3 times minus 10, and then 7 5s are 35, but then minus 5 from the last element, 0 again. Aha! So it has, in fact, passed both of our tests, and we're now very confident that's correct. This is a great test to do. One word of warning, though, the one thing it won't pick up is if you've done your rising and falling diagonals in exactly the wrong way round by starting with the wrong pattern. So do remember the VNV pattern, and this test will check for any particular slips in your multiplications. And that's the end of the video. Okay, so in this short video I'm just going to look at 4 more examples of the cross product for practice, and here they are. Okay, so here's the first one. We want the first element of this cross product, so we ignore the first elements of the two source vectors. We do the falling diagonal, 3 times 0, that's 0, and we subtract the rising diagonal, 7 times minus 1, that is minus 7, so we're subtracting minus 7, that means we'll get plus 7. So the first element here is going to be a 7. Okay, so now we want the second element. That means we ignore the second element of the two source vectors. We do, however, the rising diagonal first. 7 2 is 14, minus 1 times 0 is 0. So that's 14. So the second one was the rising diagonal first, if you follow me. And then finally, to get the third component, we ignore the third component of the source vectors, and we do the falling diagonal. 1 times minus 1 is minus 1, minus 3 2s are 6. So that is minus 7. Okay, so there's our solution, 7, 14, minus 7. But is that correct, or have we made a slip? it's a good time to check the old dot product trick. So if we call this A cross B equals C, then we should find that if we do the dot product of one of the input vectors, say B, with C, then it should be 0. Let's check that. 7 2s are 14, minus 1 times 14 is minus 14, 0 times minus 7 is 0. So that's 14 minus 14. It's correct. Let's do the other one. It's harder. So 1 times 7 is 7, 3 times 14 is 42, so that's 49 in total. And then the final term here, 7 7s are 49, but that was with a minus number, so we've got, in fact, 49 minus 49 is 0, so another one of those dot products is correctly 0. So what we found out is that A dot C and B dot C are both equal to 0, as they must be, so we're now very confident that we have the right cross product there. Let's do another one. Okay, so we're going to want the first element, so we ignore the first element of the two source vectors, and we do 8 3s are 24 minus 2 times 1 is 2, so that's 22. Let's do the next element. So we ignore the middle elements and we do the rising diagonal. 4 2s are 8 minus 8, that's just going to be 0. And then finally we ignore the bottom elements and we do the falling diagonal minus the rising diagonal. 1 minus 12 is minus 11. So there's our solution, 22, 0 minus 11. We notice we could take 11 out of that as a common factor. That would make the next stage very easy, but let's just let's do it the hard way and do the dot product. So 4 times 22 is 88, 1 times 0 is 0, and minus 88. Actually pretty easy to confirm that's 0. Let's do the other one. 1 times 22 is 22, 3 times 0, and again 2 times minus 11, again 0. So that's fine. That one's passed its checks as well. On to the third one. Okay, so this time I think I might take a common factor out just to show us doing that, because I see that this 25, 5, 15 chap is going to lead to some pretty big numbers. But maybe I don't need to do that. I can just take the common factor of 5 out of the first vector. We're calling it vector A. So that's just 5, 1 minus 3. And then I go ahead and write vector B, which can't be simplified as just 1, 3 minus 2. We'll do this cross product, and then we'll put the factor of 5 in at the end. That's fine to do it that way round. Okay, so let's go ahead and write that out. There's our factor of 5, and here's our cross product. So the first element of our cross product, we ignore the first elements of the two source vectors. We do the falling diagonal, that gives us a minus 2. We subtract the rising diagonal, that's a minus 9. So that's minus 2 plus 9, that's going to give us a 7. And now the middle element, we ignore the middle elements on the two source vectors. We do the rising diagonal this time, gives us minus 3. We subtract the falling diagonal, that gives us minus 10, which means we're going to have to add on 10. So that's minus 3 plus 10, it's another 7. Okay, and then finally, the third element, we ignore the third elements on the source vector. We do the falling diagonal, that's 5 3s are 15, and we subtract the rising diagonal 1. That's going to give us another 14. So in fact a really simple vector here, because we could take out a factor of 7 if we want to, but let's check those dot products. Do it before or after we take out the factor of 7. It's pretty easy. That's going to be 4 times 7 minus and minus 2 times 14. Yes, that goes to 0. Let's do this one just quickly. 35 and another 7 is 42, but minus 3 times 14 is exactly minus 42, so that one is also satisfied. We've passed our checks. That looks pretty good. We can leave it like this, or if we want, we can take out that factor of 7 and do 35 times 1, 1, 2. Very simple, very nice vector there. Okay, let's come here now, come down to the bottom and look at the final one. We notice it's actually the cross product of a vector with itself. It's the same vector here. So what are we going to get? Well, we can just easily enough work it out. We ignore the first two elements and we do 2 times minus 4 and minus 4 times 2. So it's something minus itself. That's just going to give us a 0, obviously. And let's keep going. If we ignore the middle terms and do the rising diagonal minus the falling diagonal, again, 3s and minus 4s, the same product. So something minus itself, 0, and it's going to be the same for the final element. So the cross product of a vector with itself is always going to be the 0 vector. Now, it's important not to write that just as the scalar 0 because it is a different object. It's the vector 0. It's a set of, in three-dimensional space, 3 zeros. So that's what we get when we cross a vector with itself. Of course, this is going to trivially satisfy our condition on the a.c is equal to 0 and b.c is equal to 0. That's clear. And so I think that's a nice set of 4 examples done quite quickly there. They're not too bad, are they? So that's the end of the video. Okay, in this video we're going to look again at the cross product, but this time we're going to ask about its geometric meaning and its properties when we come to manipulate it. Okay, so if some vector c is the cross product of two other vectors a and b, we've already seen how to work that out. But what we can reasonably now ask is, what does that vector c look like? You know, if we imagine a particular couple of vectors a and b there in space, where is this vector c? How is it related to them? We know how to work it out, but what's its relationship with them? How should we think about it? And that's what we're gonna figure out now. So we know that c is a vector, so it has two properties. It has its magnitude and direction. Let's think about the magnitude first. What is the magnitude of c, and how does that relate to a and b? What is the length of that vector? It's pretty simple. The magnitude of c is the magnitude of a times the magnitude of b times sine of the angle between a and b. This is very similar to the dot product, except with a sine instead of a cos. So there we are. There's our two vectors a and b and an angle between them. And from those magnitudes, the lengths of those two vectors and the angle, we can work out the magnitude of c. Note that if we cross a vector with itself, the angle will be 0, and so the cross product will be 0, just as we've already seen in our examples. That was easy enough. What about the direction of this new vector c? How does that relate? Okay, here's the thing. The direction of c is perpendicular, sorry for my writing there, wiggly writing, c is perpendicular to both vectors a and b. So it's at right angles to each of those vectors separately and simultaneously. What does that look like? Well, actually, we can draw it in one of two ways, one of which is right and one is wrong. Let's just do that. So here's our vector a, here's our vector b. If we draw c like that and make it clear with this little symbol that it's at right angles to those two vectors, that would be perpendicular to them both. How about this? We could also draw vector a, draw vector b again, and we could go in the opposite direction, simply literally the opposite direction, and that would also be perpendicular to these two vectors. One of these is actually strictly the correct case, and the other is wrong by essentially a minus 1 multiple. What's the way to work that out? So let's now figure that out. There's actually a rule to remember it by. It's called the right-hand screw rule. So let's draw that out kind of really clearly one more time. We have two vectors, a and b, and we are going to say that a cross b is equal to some vector c. That's fine. So what we do is we put on the line along which we know c must lie. So this is the line that's perpendicular to both a and b. And we simply have to ask ourselves, in this picture, does the vector c go upwards or does it go downwards? The trick is to write on the angle between a and b and give it a direction so that it's increasing from a to b. It's the angle from a to b. Then you imagine taking your right hand and gripping that line in such a way that your fingers curl in the same direction as the angle increases, and then your thumb points in the direction that in the actual direction of c. Let's do another example just to really make that clear. Here's a and b again. So we know we need to be I've drawn these lying in a plane, so I'm now trying to draw a line that's perpendicular to that plane. Vector c must lie in one direction or the other along this line. What do? We draw on the angle. We now take our right hand and we imagine gripping that line we've just drawn in such a way that our fingers curl in the direction in which the angle is increasing. So it's like the anti-clockwise direction in this picture, and then our thumb points in the correct direction for that vector. So it's in fact these are the two opposite cases. So that's the rule. That allows you to construct the correct direction for your vector geometrically. Okay. Then let's just finally wrap up by thinking about the cross product and asking whether it has those properties that we looked at before for vector addition, the commutative property. So for example, is A cross B equal to B cross A? It is not. It is not equal to it. Unlike the dot product, unlike addition, this one, the cross product, it matters the order, and in fact it simply introduces a minus sign if you swap the order of A and B. So it's not commutative. It nearly is, in the sense that it gives you something similar. It gives you the same thing up to a minus sign. It's important to remember. And you can just verify that by thinking about how we work out A and B with those diagonal products. Now, how about the associative property? Can we say that A cross B cross C, where B and C have already been worked out, is the same as A cross B and then cross C? What do we think? Is that going to work or not? In fact, this is the associative property. We might ask whether this is true, and the answer is no. Again, the cross product does not have this property, so the order in which you do your cross product, if you have doing the cross product of three vectors, does matter. We can easily convince ourselves of this just by looking at a particularly convenient example. Let's just use Cartesian vectors ijk. So let's just remind ourselves where these guys lie. They're perpendicular to each other. I, j, and k just are unit vectors going in the x, y, and z direction. So suppose we have this guy I cross k. If we try evaluating it this way round, with the I cross k being worked out first, well, that's just going to give us, in fact, minus j, which you can confirm with the right-hand rule that we just introduced. And then that, in turn, will give us k. That's fine. So we've worked out, in that instance, the answer is minus k. Now let's do it the other way round. I cross I, if we do that first, that's just going to be 0 because I cross I is 0, so it's game over already at that point. So we can see two radically different answers here, just depending on our order. Finally, we could ask about the distributive property. So are we allowed to multiply through using the cross product if the second object in our cross product is a sum of two vectors? Can we do this? Well, this at last is something that we are going to be allowed to do. It is the distributive property, and the cross product operation, the vector product, does have this property. We are allowed to do that, but of course we must make sure to keep the order the same. Okay, so I think that's everything for this video. Okay, in this lecture we're going to be looking at something called the scalar triple product. So what we're dealing with here is taking three vectors and combining them in a certain way in order to yield a single one scalar quantity. So three vectors into one scalar triple product. Suppose we have A, we dot it with B, which itself is crossed with C. That is the scalar triple product, that combination. Now here I've put brackets to emphasize to do the cross product first. But we can just write A dot B cross C without the brackets. Why? Because we have to do it in the correct order. If we try to do A dot B first and then cross that with C, it's a nonsense, because that will be a scalar cross-producted with a vector. Doesn't make sense. Alright then, so let's do one. We'll make up some vectors. Let's have A is equal to 3, 1, minus 1, and B is equal to 2, 0, 4, and C is equal to minus 1, minus 2, 3. Okay, there are our vectors, and let's go ahead and work it out. So first we'll need to do the cross product B cross C. So let's write that out. So I'm bringing these down now. Remember, you can work out the cross product by whatever your favorite method is. I'm just going to do it in the method I introduced before, which is we ignore the first elements and we do the falling diagonal, here 0, and subtract the rising diagonal -8. That gives us the first element of 8. Then we ignore the middle elements and we do the rising diagonal, gives us -4, subtract the falling diagonal, which is 6, so that's going to give us a -10 entry. And then we ignore the third elements and we do the falling diagonal, gives us a -4, and subtract 0, so that's going to be -4. That is our candidate for our cross product, but it's always good to test. How do we test a cross product? We try dotting it with either of the input vectors and check we get 0. So here we'll get 8 2s are 16 and 4 minus 4 is -16. Add it up, that is 0. And now we try the other combination. Here we're going to have -1 on 8's -8, and then +20, and then -12. That does indeed add up to 0. It's passed our checks. Those were just checks, but it was good to do them. And so we're now very happy that that is the correct cross product. To finish the scalar triple product, we now just need to dot that with A. So let's write it out again. -10, -4, and do the dot product. That's 24 minus 10 plus 4 is going to be 18. That's the answer. That's our scalar triple product. It could have been a positive number, a negative number, it could have been 0. In this case it's 18. Now let's do another one, so I'll erase this, but we'll simply use the same 3 vectors, but we'll do them in a different order as our second example. So let's do B dotted with C cross A. So of course we have to start by doing that C cross A combination first. So let me write that down quickly. -1, -2, 3 crossed with 3, 1, -1. So we start with the falling diagonal, that's going to be 2, and then we subtract 3, that's -1. And then we have a rising diagonal, that's going to be 9, and subtract 1, that's 8. And then we have a falling diagonal, -1, and subtract -6, so that's going to be 5 in all. Okay, did I get that cross product correct or not? Do the dot product test. -3, there's a dot product test, -3, 8, -5, that one's passed. Let's try this dot product combination as a second check, double check. 1 minus 16 plus 15, that's also going to come out at 0. So it's passed both of my checks, that one is 0 as well. We're happy that this is indeed the cross product C cross A. We now need to complete it, so what we're doing is B, which was 204, dotted with what we found, our cross product, -185. So we go ahead and evaluate this, -2, 0, and 20, 18 again. Alright, so our second example has also given us 18. Does this mean that it doesn't matter in which order we do the elements of the scalar triple product? Let me just write down the answer to that, and then we'll look at it. It turns out that for any vectors A, B, and C, then A dot B cross C is equal to B dot C cross A. These were the two cases we looked at, and it's also equal, in fact, to C dot A cross B. This will always be true. In this case, it was equal to 18. But these three things will always be equal. There are 3 other combinations we could write down in principle. There are 3 other ways to combine A, B, and C. We could have A dot C cross B, or we could have B dot A cross C, or we could have C dot B cross A. Now it turns out that those things are easy to see what they will be, because let's just look at the difference from the ones above. I've just swapped the order of the cross product, and we know that when we swap the order of a cross product, we introduce a minus sign. So if the top 3 cases were equal to 18, the bottom 3 cases must be equal to each other and equal to minus 18. And in general, this is the same rule for all scalar triple products. 3 of them are equal, and 3 of them are equal to one another, but equal to the minus of the first 3, so to speak. And how can you tell which ones are equal? It's helpful to write out this little cycle, A, B, and C, written in a circle like this. if we are going around in a clockwise direction, here B dot C cross A, but that's clockwise around our wheel, then and here's another one that's clockwise, C dot A cross B, those guys all belong together. So the guys that are in the clockwise direction all belong together, and the anti-clockwise guys, they belong together, and they're the minus of one another, these two groups. Alright, so that's I think all we need to do as practice for doing the scalar triple product and knowing what we ought to get. Let's think about something else. I'm going to introduce you to something called the parallelepiped. That's the way I say it. I'm not sure how to pronounce it. Parallelepiped. Anyway, this guy is a three-dimensional shape. But first, I'm going to remind you of what a parallelogram looks like. So here's a rectangle, and here's a parallelogram that we get if we have the pairs of sides are parallel to each other, but they are not at right angles around the vertex. Now consider this rectangular box, and let's tidy it up. There we are. And consider what happens if we build it out of edges that are in groups of parallel edges, but are not all at right angles to each other. So let's see if I can draw this reasonably realistically as a three-dimensional object. So I'm going to draw this, and then I'm going to stress which edges are parallel to each other. Alright, here we are. Okay, let me change color. So consider these four edges of the object are all parallel to each other in exactly the same way that in our simple parallelogram these opposing edges were parallel. And then these four edges are all parallel to one another again in our 3D shape, just as these two edges are parallel. And then we have another set. These four edges here in yellow are also going to be parallel to one another. That object is a particular three-dimensional solid. It's clearly a generalization of the box, in that we're allowing ourselves to have slanting edges if we want to. Now let's introduce three vectors, A, B and C, to represent these three kinds of edges. You see that all the green edges are the same vector A, and so on. What happens if we do A dot B cross C? That, it turns out, the magnitude of that, if we drop the sign then, the magnitude is just the volume of this shape. So it contains of course, the simple case of a rectangular box as a special case, but this will work for any parallelepiped that we care to think of. The three vectors can always be combined with the scalar triple product to give us the volume. And that's the end of the video. Welcome to the third topic in this video series, where I'll be introducing the matrix and thinking about what is a matrix product. Alright, so essentially a matrix is nothing more than a grid of numbers. Simply a grid of numbers that could be positive or negative or fractional or zeros. And when we specify the shape of our grid of numbers, we do so simply by stating how many rows we have and how many columns. So we're going to hear about rows and columns a lot in this video. In this video course, I'm going to use a particular way of writing a matrix as a symbol. When I need to do that, I'm going to just use a capital letter, and the letter is going to be double underlined. I'll double underline that symbol. So here we go. A underline, underline. That means the matrix A. And how would we write it? So let's just like this, essentially a grid of numbers, and we put it in curvy brackets just to give it some structure. So this is 3 rows, 2 columns, that one. Here's a matrix B. Let's make it a square matrix. Let's put in a fraction to show we can. -10, 0. Okay, so there are 2 different examples of a matrix. Easy enough, but it gets more interesting when we try and combine them. So I want to talk about matrix multiplication. Addition is simple and it's just element by element addition, but multiplication is not so simple. So here's how we write it. the multiplication of matrix A by matrix B is simply written like this, AB, and it gives us some new matrix C, which may be a different shape from both A and B, as we'll see. Let's give ourselves a couple of examples. 3, 0, minus 1, 2, 3, 4, and matrix B can be just 1, 2, 0, minus 3. So there are our two matrices. Here I've chosen them such that AB, that multiplication, will work. It will exist. But actually, if we try it the other way round, it will turn out that the multiple of those two matrices doesn't even exist. It's not a well-defined thing. So this is an extreme case of an operation not being reversible in its order. In other words, matrix multiplication is not commutative. Okay. So let's just erase that and go ahead and see how the multiplication actually works. The trick is to multiply each row of matrix A, the first matrix, by each entire column of matrix B. What does that mean? Well, let's write out our example: 3, 2, 0, 3, minus 4, minus 1, minus 1, 4, 1, 0, 2, minus 3. Now I know that this guy is going to have 3 rows and 2 columns, the output matrix. You'll see why in a bit. I'll just put these blanks in for now. The question is how to work out each of these numbers. Let's choose this one first. Okay. Now notice this guy's address, if you like, is row 1, column 1 of the output matrix C. I'm going to need to, in order to work this guy out, I'll need to look at the whole of row 1 in the first matrix, in matrix A, and the whole of column 1 in the matrix B. I'll need to combine those guys. And how do I combine them? I just multiply element by element as I go along the row and down the column. So 3 times 1 just gives me 3, and then I add on the next combination. 2 times 2 is 4, so 3 plus 4 is going to give me 7. That's how I combine those two. I'll jump back here and I'll erase there, and I'll just put in my 7. Alright, so that's the general way it works. Let's go ahead and do the other elements of our matrix C. Let's do this one. Notice this is still row 1, so I want that first row. It's now column 2, that's its address, so I want the second column. 3 times 0 and 2 times minus 3 is how I'll work that out, and that's just going to be minus 6. So let me jump backwards and erase my blank symbol and write in minus 6. Okay, maybe I went a bit fast. Let me spell this one out more explicitly. Okay, so here I now have row 2, column 1, that's the address of that guy. I want all of row 2 and all of column 1. I want to look at those guys and I want to multiply along. So 0 times 1 and 3 times 2, that's going to give us just 6 in total when we add them up. So let me erase and put in 6. And now this element, that's row 2, column 2. So I want all of row 2, I want all of column 2. I multiply 0 times 0, and 3 times minus 3 is minus 9, so that's going to be a minus 9 if I go backwards and just put in minus 9 here. Now we're finally on to the final third row, so we're going to want the third row of A, and in this case the first column. So that's 1 times minus 1, and 4 times 2 is 8, that's going to be 7, minus 1 plus 8, and then finally, last row, last column, 4 times minus 3 is 12, and a 0, minus 12. Alright, so there we are. That is our matrix product C, formed by combining each row and each column. It's quite a lot of work, and it would be even more if we had bigger matrices. But we said that we get something quite different if we try multiplying A and B in the other order. So let's go ahead and do that now. What if we have 1, 0, 2, minus 3, that's B, onto 3, 2, 0, 3, minus 1, 4, that's A. So we can try it, we try it and multiply row 1 by column 1, and we immediately find that we cannot, because they are a different length, a different list. So there is no third element of our row to multiply with our third element of the column. Just pause the video here and have a look at that and see why that must be impossible for us. And so sometimes matrix multiplication is impossible. Alright, let's look at a few little further examples, and you may want to pause the video to convince yourself in each case it's true. Is this thing possible, for example? Pause it and think. This one is not possible. This is not possible, again, because there are two elements in, say, the first row of A and three elements in the column, single column of B. There's no way to do that as a series of element by element products. How about this? We just have this row matrix and this column matrix. Can we do that? Yes, this one is perfectly possible. Actually, it just produces a single number. In fact, it's a bit like a dot product. It's the whole of row 1 times, which is the entire matrix, and then the whole of column 1 in B. This thing is called a row matrix, and this other guy is called a column matrix for obvious reasons. Okay, how about this? Let's have a look at this one. What if I swap the order of my row and column? I just swap them around. Can I do that? Is that going to produce a legitimate matrix? Actually, yes it will. This time, swapping our two matrices A and B around has produced something which exists. It's actually a huge matrix. It's 3 by 3. It must have 3 rows and 3 columns because A has 3 rows and B has 3 columns. How does it work? Let's look at that guy, for example. It's just simply the number there, which is row 1 is just a number and column 2 is just a number, single number, so we just do that product. There's no problem. Pause the video if it's confusing. Alright, so again, the point here is that A times B is generally not equal to B times A. Even if they both exist, they may not be the same, they may not even be the same shape. However, we can go on and ask about the other kinds of properties of the matrix product operation. A onto B times C, is that the same as A times B onto C? Does the order matter? Actually, it is the same. It does work. In other words, we have the associative property. How about A into B plus C, sum of two matrices? Yes, we can have A onto B plus A onto C. That is therefore the distributive property. Matrix multiplication does satisfy those things. It's just not commutative. Okay, let me make a bit more room up here in the top of the screen and put one final puzzle up. Suppose I have this 2-row 3-column matrix and then a mystery matrix M, and then I have a simple column matrix of 2 rows, and I'm asking what shape should matrix M be, or is it possible? Pause and think about that. And in fact, it's just a column matrix of 3 elements. You may want to just meditate on that and see that it's correct. Okay, that's the end of this video.
Okay, welcome to this video. In this one, we're going to take a look at how to work out a determinant. What is it? How can you find determinants of variance sizes? So a determinant is a scalar. It's just a number, could be positive, could be negative, could be 0, and it's derived from a square matrix. A single number derived from an entire matrix. Now, the determinant of M would be written with M with the modulus signs either side of it, even though it can be a negative number. So here's an example of M, and here is how we would write the determinant of M. Note that we don't bother writing squares, straight sides and curved brackets as well. There's no point in that. It's just enough to have the straight line sides. So let's start with the definition of a 2 by 2 determinant. That's the easy case to look at. So let's write out a general 2 by 2 just using symbols. We'll have A, B, C, D. Written inside our straight line sides indicates a determinant. It's simply AD minus BC. Okay, so that's the falling diagonal, the leading diagonal is also called, minus the rising diagonal, multiplied together. Very simple, and that is how you can just look at and evaluate a 2 by 2 determinant. So for our example, 1, 2, 3, 4, 1 times 4 is 4, subtract off 2 times 3 is 6, and so that's going to give us minus 2 is the determinant. Okay, so a 3 by 3 determinant is going to be a bit more work. What we do is, when we have a 3 by 3 determinant, we evaluate it by breaking it up into a number up to 3 smaller determinants, each of which is a 2 by 2, and for that we have our definition for immediate evaluation. So we break up bigger determinants into little ones and then evaluate them. Now I'm going to write out something here that's like a chessboard, but instead of black and white I have pluses and minuses. You'll see why in a moment. The thing to notice though is that we alternate plus minus along each row and each column in this 3 by 3 grid. Okay. So now let's work out a 3 by 3 determinant. Again, I will just use general symbols A, B, C, D, E, F, G, H, I. Right. Now first I have to choose a row or a column. I'm going to choose this top row for the first example. And I'm going to work along this row. And I'm going to start with the A symbol. Now I go and I look on my chart and I see that there's a plus sign in that slot of my grid. That means I put down plus A. And now what I do is I ignore the whole row and the whole column that A is in, and I look at the remaining 4 numbers and I write a little determinant just made out of those guys in the same order they appear. So EF is going to be in my main determinant there, and HI. Those are the remaining 4 guys in the same order they appear. Now B, the next term, that has a minus sign according to my chart, so I will put in minus B and multiply it by, again, a smaller 2 by 2 determinant, the one I get if I delete the row and the column with B in it and look at the remaining guys, D, F, G, I, and I just write those guys out in the same order they appear as a small 2 by 2 determinant. Finally, there's C. C appears with a plus sign according to my chart. So I need to put down plus C, and I need to multiply by, well, we delete the row and column with C in it, and we just see the remaining determinant D, E, G, H. So I simply imagine that row and column was not there, and then that's what the determinant becomes. And then of course those 2 by 2 determinants, I can just write down what they are using my rule of multiplying down the diagonal and of subtracting the anti-diagonal. Okay, there we are. So that is, in general, what a 3 by 3 determinant evaluates to. But it's not the only way to do it. Let's write it out again, and this time let's choose a column and a different one. Let's choose this column. I'm also allowed to work down this. So I would start with B as my first term, and I delete the row and column with it in, and I'd see what are the remaining terms and write them D, F, G, I. Except I've forgotten something. There's a minus sign attached to that particular entry, so that should actually have been minus B. Alright, and then similarly plus E, and I delete the row and column which has E in it, and then I just make a 2 by 2 determinant from, in this case it would be the corner elements, A, C, G, I. And then finally minus H, and delete the row and column with H in it, make a 2 by 2 determinant of what's left, A, C, D, F. Okay, and of course I could then write out these 2 by 2 determinants explicitly. But the point is, it will give me the same answer. Let's do an example and see why we would choose one method or the other. So here are just some random numbers I'm making up. Let's stick that in. It's 3 by 3. First off, let's work along the top row, and as we did in our first example. So that's going to be 3. Let's put in the full determinant here, and then minus 1, and again the determinant I get by excluding the top row and middle column, and then plus 2. That's going to be 7, 0, 5, minus 1. And I can go ahead and I can work out explicitly what this comes out at, as you can see I'm doing here. And in fact it will be 12 plus 20 minus 14, and it comes out as 18. So there we are, we've worked out a 3 by 3. But we could have done it in a different way. Let's say we went along this bottom row. That's fine. So then it will be 5. and I will be left with 1, 2, 0, 4 for my mini determinant, and then the next element along, a minus sign, and it was a minus number anyway, minus minus 1, that's going to be 3, 2, 7, 4. Let's just see how we've done that. 3, 2, 7, 4 by deleting the bottom row and middle column of that. Now what about the third element here? Well, we actually have a 0 plus 0 times some determinant. I don't even care what that is because it's been multiplied by 0. That's the beauty of it. So I've got 5 into 4 minus 0, and then we're going to have 4 3s are 12 minus 14. So that's going to give us 20 minus 2 is 18. Same answer as before. Okay, what about if we have even bigger determinants than our 3 by 3 example there? If we go bigger still, for example, a 4 by 4, we're just going to break it up into a number of 3 by 3s, and each of those would have to be broken up into 2 by 2s. Lots of work. So here we are. Here's a general 4 by 4. We are going to expand it along a row or column. Let's say we want to expand it along this row, for example, and we'll take in turn A, B, C, D. And we'll need to know what sign to use. So here's our checkerboard or our chessboard pattern of pluses and minuses, just extended out now to a 4 by 4. And you can see the rule here is that if the row number plus the column number is an even number, then there's going to be a plus sign. And if it's odd, it's going to be a minus sign. You can confirm that for yourself. Look at this one. It's going to be at row 2 and column 3, and that's 5. And so that's a minus. That's one way to remember it, or just draw it out. Anyway, we're going to use that rule, so we go ahead and we write plus A, and now we need to do the entire 3 by 3 determinant that we get when we delete the row and column with A in it. So we just write out that little square block that we see is quite easy to copy across. And now we're going to have minus B, and we need to delete the row and column and then transcribe across the elements that are left as a 3 by 3, just being careful not to make any slips. And you see that we're going to continue to, so let's delete this just to be completely explicit. I'll finish the job off. So I hope it's obvious what we're doing. We're on to plus C, and now we're going to just have E, F, H, I, J, L, and M, N, P, and then finally minus D onto what we get if we delete the top row and rightmost column, which is left over then E, F, G, I, J, K, M, N, O. There we are. That's how we handle a 4 by 4. Each of these 3 by 3s would then have to be evaluated and so on. So a lot of work. And that's the end of the video.
Okay, welcome to this fifth topic, which is eigenvalues and eigenvectors. We'll introduce the problem and we'll see how to find eigenvalues. Finding eigenvectors is for the next video. So suppose that we are given a square matrix, M, just some matrix, but we are told that M multiplied by V is equal to lambda multiplied by V for some scalar, just some number, lambda, and for some column matrix, V. And a column matrix, of course, the same as a vector. I will just say vector from now on. Okay, so this scalar lambda could be positive, negative, or 0. Meanwhile, this vector V could be anything except the trivial boring case of just zeros. It's something other than that. Our challenge then is that we're going to be given a square matrix M, and we have to look for any scalar lambda and vector V that satisfies the equation. And such a scalar is called an eigenvalue, and such a vector is called an eigenvector. So in that language, M multiplied by some eigenvector gives us back that eigenvector just multiplied by a scalar, the eigenvalue. Okay, so first off, let's notice that if we are given a candidate, a possible eigenvector V to try, perhaps for a multiple choice, then it's easy to test. We'll just go ahead and try it. So here's a square matrix, a 2 by 2, 2, 4, 1, minus 1, and suppose we write down V is equal to 1 minus 1, and this is suggested as a possible eigenvector. Well then, we would just test it out to see if it matches our equation. we'd try multiplying m by v. So here we go, 2, 4, 1, minus 1, and v is 1 minus 1 as a column. And so we do row times column, that's 2, and minus 4 is minus 2. And again, row and column, that's going to be 1 plus 1 is 2. And we notice we can take out minus 2 as a factor, and then it will be the vector left is 1 minus 1, but that is just v. So minus 2 is indeed a scalar that multiplies v, and we've succeeded in proving that v is our eigenvector, and our eigenvalue that goes with it is minus 2. Okay, so that's great if we're given eigenvectors to check out, but what if we're not given any eigenvectors or eigenvalues? Then we must find any possible eigenvalues for ourselves. There could be more than one, and for each we must find the corresponding eigenvector v. And in this first video we're just going to be finding those eigenvalues. Okay, so here's a little bit of quick manipulation and aside. We know that our equation is mv is equal to lambda v. I can certainly just bring it all to the left hand side and write mv minus lambda v is equal to 0, as long as I remember to write that as vector 0. But now let's do something interesting. Let's insert the identity matrix, which won't change the equation, but it will be important for the next step. mv minus lambda times the identity times v is equal to vector 0. The identity doesn't change the equation, but now I can factor out both those two matrices, the m and the minus lambda times the identity. That's a matrix. I can factor those out, and it allows me to write that line. Now, that form of the equation, it turns out this can only be solved for any interesting v, any v other than just zeros, if the following equation is true, which we can easily prove, but we're not going to prove in this video. M minus lambda times the identity, the determinant of that is equal to 0. So we're going to have plenty of time to think about that, but let me just put a green box around it, because that is the fundamental equation we're going to use. This will allow us to find all the eigenvalues that satisfy our basic eigenvalue equation. So let's do an example. It's the best thing. Let's do m as a 2, 4, this was the one we had before, 2, 4, minus 1, little square matrix. And so let's write down what this lambda times the identity is. For a 2 by 2, it's going to be lambda, 0, 0, lambda. Very simple. And so this matrix that's the difference of the two of them, 2 minus lambda, 4, 1, minus 1 minus lambda, just the difference of those two things as a determinant, is equal to 0. That's all. So there we have it. We've just subtracted lambda off down the diagonal, but now we need to solve this. So we just write out the determinant, 2 minus lambda multiplied by minus 1 minus lambda down the diagonal, minus 4, the off diagonal, is equal to 0. Alright, so we expand this out. Minus 2 lambda plus lambda squared minus 4 equals 0. Let's come over here for a bit more space, tidy that up a bit. What have we got? Lambda squared minus lambda minus 6 is equal to 0. Can we solve this? Actually, it's quite easy to factor. That's going to be lambda minus 3 into lambda plus 2 is equal to 0. So that's true if either lambda is equal to 3 or it's equal to minus 2. And those are our two eigenvalues. We found them using that equation in the square box. Let's crack on and do one with a 3 by 3 matrix M. Here we go. Matrix M is equal to, let's have minus 2, 1, 3, 1 minus 1, 0, and minus 1, 1, 2. I've worked that one out. I've checked that before and it will work for us nicely. Now, let's remember, of course, the rule from the previous screen, and we just need to apply that. So let's go ahead and write it as write our determinant out. We need to have minus 2 minus lambda, and then just 1 and minus 1, and then 1 minus 1 minus lambda, and then 1, and 3, 0, 2 minus lambda. I'm just subtracting lambdas down the diagonal, making it a determinant, setting it equal to 0. Now I'm going to work along this row because it's got a 0 in it, so that makes me like it a bit more as a determinant. The first number is going to be minus 1. Why? Because it's a 1, and let me just quickly write out our little lookup table of pluses and minuses for doing determinants. So it was a 1, and then it picked up a minus sign, and then we have the mini determinant that's made out of those 4 terms. So that's 1, 3, 1, and 2 minus lambda. Alright? And then the next term is going to be plus, and then it's going to be, the term itself is minus 1 minus lambda, and the mini determinant that we get when we exclude that row and that column is just made out of the corner terms. That's going to be minus 2 minus lambda, and 3, and 1, and 2 minus lambda. And that's it, because the 0 term gives us nothing. So it was only those 2 mini determinants. Let's write them out. Minus 1, 2 times lambda, and then 3 times 1 is 3. Let's expand that one out. And then this one has the term in front, minus of 1 plus lambda, and then we have to expand out the determinant, minus 2 minus lambda times 2 minus lambda down the lead diagonal, minus 3 is plus 3, there we are, is equal to 0. And then we just need to tidy that up. We need to clean it up a bit. That's going to be minus of minus lambda minus 1 for the first term. Let's turn that all into pluses, multiply through by the minus 1. And here we have minus, let's make that lambda plus 1, write it that way round, and then tidy up inside here, we expand it out, minus 4 plus 2 lambda minus 2 lambda plus lambda squared, and this 3 is equal to 0. We need to keep on working to tidy that a bit more. This term here is in fact going to be just, I see the lambdas cancel out, lambda squared minus 1, that's very nice, that's come down very, very neatly. So now we can really tidy that up, and we can take out a common factor of lambda plus 1, and the first term was just that, so there's 1 for that. And the second term we've just found is lambda squared minus 1. Pause the video and check you agree that that's a tidied up version of the equation. Now the way that can be 0 is either the first term is 0, which requires lambda is equal to minus 1, so there's one eigenvalue for us, that's one option. One of our eigenvalues has been found. Or the second term here has to be 0, so let's do a bit more work with that. What we're saying is, to neaten that up, we're saying that 2 minus lambda squared is equal to 0. In other words, lambda squared is equal to 2, and so lambda is going to be plus or minus square root of 2. That's 2 more eigenvalues, 3 in all, that we found for this 3 by 3 matrix. And in the next video, we'll see how to take each of these values and derive the corresponding vector. This is the second of 2 videos that looks at eigenvalues and eigenvectors. In the first video, we have seen how to find eigenvalues, and we write these as lambda. For each lambda, how do we find the eigenvector, an eigenvector, that goes with it? We know that our fundamental equation that we're working with here is that when matrix M multiplies an eigenvector V, it just gives us back that V scaled by lambda. And another way to write that is that M minus lambda times the identity multiplied by V is equal to vector 0. This is the same equation written 2 different ways. What we need to know now that we have obtained our lambda values, we just need to look at one of these equations and figure out an acceptable vector. I find that it's more useful to use the form on the right-hand side. Okay, let's look at a particular example. We'll have the matrix 2, 4, 1, minus 1. We looked at this before, and we found already that its eigenvalues are equal to 3 and minus 2. What we're going to do now is we're going to take those values one at a time and figure out an acceptable eigenvector. We're going to write our vector that we need to find as just x and y, where we need to find these xy values. Now take a look at this green underlined equation, and in particular the matrix, which is a difference of 2 different matrices, M and lambda times the identity. Now that we have our lambda value of 3, we could write out that difference matrix. It's going to be 2 minus 3, and then just 4, and then just 1, and minus 1, minus 3. There it is. And we're saying that when that multiplies our vector xy, it gives us 0, 0. So let's go ahead and clean this equation up. We have minus 1, 4, 1 minus 4 onto x and y. If we want to be explicit about that, we can multiply out. It means minus x plus 4y and x minus 4y, and that we know is equal to 0, 0. Now what we immediately notice here is that whilst this equation between two column vectors is telling us two things, it's actually telling us the same equation twice. So we can see here that we're saying minus x plus 4y is equal to 0. And we're also saying that x minus 4y is equal to 0. That's telling us the same thing. Is that a problem? No, that's exactly what we want to see at this stage. We should find that when we work on eigenvalue and eigenvector problems based on a 2x2 matrix, then really only one of these rows in the final expression constrains us, and the other one doesn't add any new constraint. So this is exactly what we want. So now, how do we go ahead and solve it? We're saying that minus x plus 4y is equal to 0. Of course, we can just rearrange this to say instead that 4y is equal to x. And that's the only constraint we have. What we're allowed to do is choose, we can choose the simplest values of x and y that will make this work. So I'm going to choose y is equal to 1, and then I'll find that x is equal to 4. And that is a perfectly acceptable eigenvector, 4, 1, to go with my eigenvalue. We will always have this freedom in choosing the elements of our eigenvector. Really, this freedom simply corresponds to choosing how long the eigenvector is, in other words, its magnitude. Because if a particular eigenvector satisfies our equations, a scaled version of that same eigenvector will still satisfy with the same eigenvalue. Now, while the eigenvector can have any length, we might specifically have been asked for a normalized eigenvector. That simply means we need to take the one that we found and scale it to have unit length. So in this case, since it's 4, 1, we need to divide by root 17 to scale to unit length. Simple as that. So there we are, that's our eigenvector and a normalized version of it. Now we still haven't found the eigenvector for the other eigenvalue, which was minus 2. Let me just move this up on the screen to make space to do that at the bottom. So here we go. We do exactly the same procedure. We subtract minus 2 on the diagonal. 2 minus minus 2, and 4, and 1, minus 1, minus minus 2. Lots of minuses there. So let's tidy that up. That's going to be 4, 4, 1, and in fact another 1. And then times xy is equal to 0, 0. As before, we see that really this is the same equation twice. There's only one constraint, and we can read it off simply as x is equal to minus y. So if I choose x is equal to 1, for example, then I'm going to write down an eigenvector 1 minus 1. Or if I'd chosen y is equal to 1, then it would have been minus 1, 1. It doesn't matter, they're both correct eigenvectors to go with our eigenvalue, but if we want to normalize, we'll need to divide by the magnitude 1 over root 2. Okay, so there are acceptable eigenvectors to go with the eigenvalue minus 2. Okay, so now let's find the eigenvectors that go with our eigenvalues for our 3x3 matrix M, which was minus 2, 1, 3, 1, minus 1, 0, minus 1, 1, 2. We looked at that before in the previous video, and we found the eigenvalues, which were minus 1, root 2, and minus root 2. And I've put little subscripts on our lambdas here so we know which one we're dealing with. Let's deal with lambda 1 first, which is the one that has value minus 1. So I'll write over here the little equation that we're using over and over again, which is that m minus lambda times the identity multiplied by our vector is 0. Okay, we need this difference matrix, so we subtract off the diagonal 1 minus minus 1, and then 1, 3, 1, and minus 1, minus minus 1, and 0, minus 1, 1, and 2 minus minus 1. And that's on x, y, and z, because we now need an eigenvector with 3 elements, and it's going to be equal to, we'll simplify the matrix to minus 1, 1, 3, 1, 0, 0, minus 1, 1, and that'll be a 3. And that again is on our x, y, z eigenvector is equal to 0, 0, 0. Now what we immediately notice is that, as before, we don't really have 3 different equations captured by our matrix equation, we only have 2. In fact, this is very obvious in this case because the bottom row is the same as the top row. That's not always the case. It's not always the case that the rows are actually identical, but we will always find, if we check, that there are only really 2 independent equations when we're dealing with 3 by 3 eigenvalue problems. We only have 2 equations, really. Now I'm going to highlight this row here, 1, 0, 0. That's just saying, in fact, that x is equal to 0. Now if we take either the top row or the bottom row, we have minus x plus y plus 3z is equal to 0, or y is equal to minus 3z. Okay, so now we simply choose any values of y and z. X has been dictated to us, but any values of y and z that satisfy these rules. So if I choose z is equal to 1, that's going to give me y is equal to minus 3. And I can straight away then write down a satisfactory eigenvector. It will be 0, minus 3, 1. As simple as that. It doesn't matter where the minus sign is. I could equivalently have chosen z is equal to minus 1, and then I'd have 0, 3, minus 1. If I normalize, then I'll need 1 over root 10, that being 3 squared plus 1 squared, and so that is a complete solution for our first eigenvector. We found it in simple form and in normalized form. This is the eigenvector that goes with eigenvalue minus 1. We can go ahead, however, and check this eigenvector to make sure that it works. So for that we'll simply need to write out our matrix M, the original matrix, which was minus 2, 1, 3, 1, minus 1, 0, minus 1, 1, 2. We have our vector 0, 3, minus 1. We just need to do this sum. So the first element is going to be a minus 2 times 0, and then as a 3, and I see there's a minus 3, so that does give us 0. And our second element is the only non-zero element will be minus 3. And our third element there gives us 1. And we can write that as simply minus 1 onto 0, 3, minus 1. And so indeed, we found that this vector works with the eigenvalue of minus 1. Now we can continue to look at, to find the other eigenvectors, but first let's take a pause and review the steps involved. So we're looking at rules for solving eigenvector problems. An eigenvector problem is where we have a square matrix M, and we say that M multiplied by some special eigenvector gives us back that eigenvector times just by a value, the eigenvalue. We find the possible eigenvalues using this equation involving a determinant of a difference of 2 matrices. In general, there are going to be n solutions for an n by n matrix. So 2 solutions for a 2 by 2, 3 solutions for a 3 by 3 matrix. That's because when we write the determinant, it will have lambda to the power of n as its highest order. So for example, we have cubed to deal with when we're working out for 3 by 3 matrices. Now, having found those eigenvalues, we then, for each value, need to figure out an acceptable eigenvector. What we've noticed is that generally we only have to use
n minus 1 of the rows in the equation that we're working to satisfy, and that meant just one row in the case of 2 by 2 problems, and 2 of the rows in the 3 by 3 problems. We had some freedom as to what values to choose for our eigenvector, and in fact that freedom corresponded to just scaling the entire eigenvector to a greater or smaller magnitude, and if we were asked to normalize, we would simply work it out using whatever values we like, the simplest values, and scale it at the last step so that it has unit length.
Okay, so we've covered a lot of ground for one video, and this would be a good place to just stop watching if you like. But I would like to carry on and solve the remaining 2 eigenvectors for our 3 by 3 example. Because they involve a square root 2, they're actually a bit more messy and tricky to do, and in a way I think that makes for a good, interesting example to see. So let me go ahead and cut back to the screen that we had before with our matrix M spelled out and our possible eigenvalues, and we'll now take the value lambda subscript 2, which is square root 2. So then, as usual, we need to subtract that down the diagonal, so we'll have minus 2 minus square root 2, 1, 3, 1, minus 1 minus square root 2, 0, minus 1, 1, 2 minus square root 2. And that is the thing which, when multiplied by our unknown eigenvector xyz, should give us 0, 0, 0. Now, one thing we notice here is the rows look all different. It looks like we've got 3 different equations captured in this matrix equation, but they are not. If we examine them carefully enough, we'd find that we could generate one of these rows from the other 2. And in fact, we're only therefore going to need to use 2 of them. You could pause the video and play with it and see if you can show this, but it must always be the case unless we've made a slip earlier. Okay, so I see that the middle row has a 0, so I'm going to start with that one. It says x plus minus 2 minus root 2 times y is equal to 0. And that means that if I choose a simple value for y of 1, then I can immediately say that x moving across is going to be 1 plus root 2. Good. So now I'll use the top line, which is minus 2 minus root 2 x plus y plus 3z is equal to 0. And I'll substitute in the values that I've already picked and inferred. So I'm going to get 1 plus root 2 onto minus 2 minus root 2, that's the x term, plus the y is 1, plus 3z yet to be found is equal to 0. Rearrange. So put z on one side, divide it by a third, expand this thing out, minus 2 minus root 2 minus 2 root 2 minus 2 plus 1. Alright, oh, and there's a minus sign because we've moved it all to the other side from the z, of course. Now we need to tidy this up, but what I notice is that inside the brackets I have a minus 3 and a minus 3 root 2, and that will cancel with a factor of a minus in third in front, and just give us a very simple expression of 1 plus root 2. So that's our z term. Okay, we've found a compatible set of x, y, and z values, so we can now write down an acceptable eigenvector, 1 plus root 2, 1, 1 plus root 2. There we are. That is an acceptable eigenvector, and here's where we found those numbers, that goes with the eigenvalue lambda 2 is equal to square root 2. Note that I used the same subscript 2 on my vector so that I make it clear that lambda subscript 2 goes along with vector subscript 2. So now our only remaining task is to look at the third eigenvalue, which was negative root 2, and find a compatible eigenvector for that one. So as always, what we need to do is take the vector m and subtract the lambda value we found off down the diagonal. And because we're subtracting a minus number, we can just add it instead, of course. So that will be minus 2 plus root 2, and then 1, and then 3, and then 1, and minus 1 plus root 2, and 0, and minus 1, and 1, and 2 plus root 2. And that matrix, when multiplied by our unknown eigenvector xyz, will give us 0, 0, 0. Now, as before, our middle row looks nicest here. It's just telling us that x plus
root 2 minus 1, put it that way around, y times y is equal to 0. That means if I chose y is equal to 1, obvious choice, then x is equal to 1 minus root 2, watching for signs. Now if I take let's say the bottom row, I can have minus x plus y plus 2 plus root 2 times z is equal to 0. But I can substitute in the values I found, so that will say that square root 2 minus 1 plus 1 plus 2 plus root 2 z is equal to 0. Okay, I've got some work to do to find out the value of z here. I'll start by rearranging just to put 2 plus root 2z is equal to minus root 2 on the other side. But I still need to do a bit more work. Divide both sides. I notice I can simplify by a factor of root 2. I can write this as z is minus 1 over root 2 plus 1. Pause the video and check you agree with me. And then I'm not happy with that because I don't want to leave z as a fraction. I could do, but that would make a very messy looking eigenvector. I notice there's a trick I have up my sleeve. I know that if I multiply the top and bottom of a fraction like that by root 2 minus 1, it will simplify. I will then find that the top, of course, is 1 minus root 2, but the bottom will be 2 plus root 2 minus root 2 minus 1, and that whole expression just comes down to 1. Finally then, z is equal to 1 minus root 2. We've now found our x, y, and z values that are acceptable. So we're saying that vector 3 that goes with the lambda 3 value is 1 minus root 2, 1, 1 minus root 2. That is an acceptable eigenvector. So we're done. For our 3 by 3 matrix M, we found the 3 eigenvalues, and for each of them, an eigenvector. The last two of these, which involved the root 2, were more tricky just because there was more to keep track of, more messy expressions, but the basic maths is the same every time.
In this series of videos, we'll talk about linear regression and least squares. And the problem that we'll be solving is, first in the most abstract setting, if you're given a subspace W of Rm and a vector, let's call it B, also in Rm, the question that we want to solve is, which vector W in this subspace W is closest to the vector B? Now, just intuitively, if we take the orthogonal projection of B onto W, let's call that P subscript capital W B, so the projection of B onto the subspace W, the orthogonal projection, we suspect that that would minimize this distance. And the distance that we're trying to minimize is B minus W. Minimize this over all W inside of this subspace W. Equivalently, you can minimize the square of the distances. And this is why this problem is called least squares, because we're minimizing the squares of each of the components of these differences when you add them all up. So that's the statement of the problem, is to find W inside of W such that the distance between W is minimized. And it turns out that the solution to this problem is exactly W equals the projection of B onto W. And I won't give a precise proof of this statement, but we should at least get an intuition for why this is true. Looking at this picture, I've already drawn the projection of B onto W and another arbitrary vector W. Now, these three vectors form a right triangle. So it looks a little bit skewed from this angle, but if you turn this way, that triangle looks something like, here's B, here's the projection of B onto W, and here's some arbitrary vector W. in the subspace W. These two vectors are in W. And so this line connecting them is also in W. The vector B is perpendicular to the subspace W, and therefore this angle is a right angle. Here, this is the hypotenuse of this triangle, and it's the distance from B to W. And this distance is the minimizing distance, supposedly. So that's just B minus the projection of B onto W. So I misused a little bit of notation here. I hope you understand that this W now is different from this one. This is the actual solution. And because this is a hypotenuse of this triangle, we know that this distance is always going to be greater than or equal to either of these two distances. No matter what W is, this will always create a triangle, a right triangle, unless W equals this vector right here. And in all other cases except this one, this distance is always going to be strictly greater than this distance. So what are some ways to compute this projection? So one way is to actually find an orthonormal basis of W. So given an orthonormal basis, let's call it W1 up to WK. Let's say K is the dimension of W. Then the projection of B onto W is just take the dot product. Remember, the dot product of B with any of these orthonormal vectors gives you the shadow of B onto that vector, and then multiply again by that vector here to give you the shadow of B onto this line in that same direction. So we take the dot product, or the inner product, I'll write the inner product with brackets, of each of these vectors, and then we'll multiply by that vector again, so that we have a vector in the end, and then sum up all of these different contributions from these different shadows. So this is how you would compute the orthogonal projection of a vector onto a specific subspace. You would need, for instance, an orthonormal basis for that subspace. But sometimes you're not given an orthonormal basis, so it might be difficult to compute it. One thing you could do is you can choose any basis of W, pick arbitrary vectors that are in W, and once you find K of them and you know that they're linearly independent, then you know that that forms a basis. Then, in order to find an orthonormal basis, you would apply the Gram-Schmidt procedure to obtain an orthonormal one. But you know how difficult that is. Maybe you can do it for the first few vectors pretty easily, but then after a while it gets pretty messy. So we'll look at a special case of this problem where W happens to equal the column space of some m by n matrix, where A is an m by n matrix, So in other words, you can think of A as a linear transformation from Rn to Rm. And in this special case, we'll find a very interesting solution to this problem. In general, when we look at this problem and we're given a vector B, so now let's suppose that this subspace is the column space of A, and we have some vector B that's not necessarily in the column space, what this means is that the linear system AX equals B does not have a solution unless A is onto, or more specifically, or more precisely, unless the vector B is in the column space of A. But because this doesn't happen in general, instead of trying to solve this system, which might not have a solution, we can solve an associated system instead that says, okay, I might not be able to find an x in our domain here that sort of maps to the vector b, because it's impossible all x's get mapped to this subspace. What instead we can try to find is project b onto this subspace, and now this vector, the projection of b onto that subspace, is by definition inside the column space of A. And therefore, we can solve that associated system. So we make a definition based on this idea that a least squares approximation to the linear system ax equals b is a solution to the associated linear system ax equals the projection onto the column space of A applied to our given vector b. And it's this problem that we'll be focusing on solving in the next few videos. Let's first state a theorem that makes it a lot easier to compute the least squares solution to a given problem in the special case that we mentioned at the end of the video in the last session. So the theorem says, given a linear transformation from Rn to Rm, that's called A, let me write it here, and a vector b in the codomain of this linear transformation, a, let's say, x in the domain that's Rn, is a least squares approximation to ax equals b. Now this is using the definition that we had made before, which remember was x is a least squares approximation to ax equals b if and only if ax equals a projection of b onto w, where w is the column space of A. If and only if x is a solution to the system A transpose AX equals A transpose B. Now, we mentioned last time that, so let me just say here, W equals the column space of A throughout this entire discussion. Now, we mentioned last time that if we have an orthonormal basis of W, we can actually solve this problem relatively easily, but in general, we're not given an orthonormal basis of W. So this formulation of the problem makes it much simpler to compute. So I said it, but I should also write this, that this means taking the transpose of this matrix. And taking the transpose is easy. You just swap the columns with the rows. So this just gives you a new linear system. And in general, this is much, much easier to solve than something like this. And the reason this simplification occurs is because we've taken our subspace to be the column space of some matrix. So before we give some examples of how to apply this theorem, we'll give the proof. If you want to skip the proof, you can go to the next video. So this is an if and only if proof. So we'll prove it in two directions. Let's first suppose that x is a least squares, suppose x is a least squares solution to ax equals b, i.e. x solves ax equals a projection of b onto w. Now, here's a little picture that'll help us visualize everything. Let's say this is the vector b, this is the subspace w, this is the projection of b onto w. If we take the difference of b with the projection onto w, so b minus the projection of B onto W, then that difference is exactly this line that's orthogonal to W. In other words, this vector is in the orthogonal complement of W. And because it's in the orthogonal complement of W, we know that no matter which vector we take in this subspace, let's call any vector here A, and the reason we're going to call it A is because A is an element in the column space of the matrix capital A, then the dot product of A with any of these vectors, with this specific vector, equals 0 for all A in the column space of A. In particular, if we take the actual columns of A, so A, E, I, let's say, and we dot, this is the ith column of A as a matrix, and we dot it with this vector, this is always going to equal 0 for all I from, and in this case, since the domain of A is Rn, it's for all I going from 1 to n. We can write this dot product using the transpose. So remember, the dot product is the you multiply each of the entries in the vectors, and then you add them all up. And the way you can express that is using the transpose of a particular vector. If we write this as a column vector, then we can write this as a row vector by taking the transpose and then matrix multiplying these entries. So we would take AEI transpose times the vector B minus PWB equals 0 for all I. But this transpose, the fact that if we look at this column of A and we take its transpose, and if this is true for all I, then this is saying that this vector is the dot product of this vector with each of the transpose vectors from A dotted with this is 0. Therefore, if we take the matrix A and transpose it, and we multiply it, matrix multiply it with this vector, it will always equal 0. And now rewrite this by moving everything over to one side. We get A transpose times the vector B equals A transpose times this projection. But by assumption, this projection, we know that X solves this equation. So we know that this also equals A transpose AX. And this shows that if X is a least square solution, in other words, if it solves this problem, then A transpose A acting on X equals A transpose B. So this proves the theorem in one direction. To prove the theorem in the other direction, I'm running out of space here, but I can give you at least the sketch of this proof. Now suppose that this equation is satisfied. So suppose X is a solution to A transpose AX equals A transpose B. We can move everything over again as we did, sort of going backwards in this calculation, and we can express this by saying that A transpose acting on AX minus B equals 0. In other words, this vector, AX minus B, is in the orthogonal complement of the column space of A. So it's in the orthogonal complement of W. Now, if we go back to our picture, we know that the vector B can be uniquely decomposed as the sum of two vectors, one a vector in W and 1 a vector in the orthogonal complement of W. So this is a theorem that you might cover in the part of your linear algebra course on when you discuss orthogonality. So B has a unique decomposition into a vector in W plus a vector, let's say in the orthogonal complement, let's call it V, where W is in W and V is in the orthogonal complement of W. But this equation here says that if we take the difference, ax minus b, and we get in the orthogonal complement, we know that this has to equal some vector. So ax minus b equals a vector in this orthogonal complement. Let's just call it v for now, because it's in the orthogonal complement. Rewriting this equation says that b must equal ax minus v. And where is ax? Ax is in the column space of A. In other words, it's already in W. So this is the vector in W. And therefore, this vector right here has to be in the orthogonal complement. And this uniqueness decomposition theorem tells us that this vector is exactly b minus ax. So this is going to look a little bit silly, but b equals ax minus ax minus b. And the uniqueness decomposition theorem tells us that this vector that's in the orthogonal complement must equal the projection of b onto that subspace W. In other words, ax, this term right here, has to equal the projection of b onto W minus this vector right here. In other words, ax equals the projection of b onto W. And that means that x is a least squares solution because it solves this equation. So that follows from the uniqueness of orthogonal decomposition of a vector into two parts. If you have a given subspace, one into a vector in that subspace, that's where this ax equals the projection of b onto W comes from, and the other vector is just the orthogonal complement, the projection onto the orthogonal complement, which is just the difference of the vector itself minus that vector in the orthogonal subspace. So this is the proof of this theorem that allows us to say if we want to solve a least squares solution problem, when W equals the column space of A, we merely have to solve this system. So the next few videos will do lots of different examples of how to actually. So the example that we'll be working out, it's quite a long example because of the generality that we'll do it in, is if you're given data, and let's say the data you're given is you have a bunch of x values and a bunch of y values. So these are one-dimensional input and one-dimensional output values. So suppose you have given data x1, y1, x2, y2, and so on, up until the number of data points that you have, xd, yd. And if you try to plot these data points, let's say they look maybe something like this. The question that you want to solve is, can you try to find a line that sort of best approximates these data? So that's the problem, is to find a best fit, whatever that means, straight line. Let's say of the form y equals mx plus b. Now, if we wanted to actually try to solve this problem, and suppose that all of these points actually lied on this line, we would want to solve this entire system. Now, m and b are our unknowns. We don't know the slope, we don't know the y-intercept. So we'd have y1, we want to set it equal to mx1 plus b. Similarly for y2, our second data point, mx2 plus b. And we keep going. yd equals mxd plus b. Now, in general, this is an over-constrained system because we have d equations, and if d is relatively large, in particular if it's bigger than 2, if it's relatively large, it's very unlikely for us to find a solution to this problem. We can rewrite this problem as a matrix equation by saying that we have the vector y, which is the vector of our data points. In fact, let me even write y as a column vector. So let's write it like y1 all the way to yd. And if we notice this, our coefficients are always being added in a linear fashion. And the only thing that's changing is the value of x1. So you could actually write this as a d by 2 matrix acting on the vector mb. Now, what should this matrix be? We want it to satisfy the equation y1 equals mx1, so x1 has to go in this column, plus b times, what's the only thing that's going to leave b exactly where it is? The number 1. And the same thing here, if we had y2, we would want to write y2 equals m x2 plus 1 times b, and so on, all the way down to xd and 1. So this matrix equation, which we can write as y vector equals a, and I don't want to write x as we did before because I don't want to conflate it with the data points that are also labeled by x. And so instead we'll write this as a xc. So this is the system that we would like to solve, but we know that there is in general no solution to this problem. So what can we do? Now in this case, the column space of A happens to be a two-dimensional subspace of R, what? Of RD. So the column space of A is a two-dimensional subspace of RD. So we can actually draw something like this, although the space it's in might be significantly larger. And we have the vector y somewhere out here. In general, it's not in the column space. In general, this line does not go through every single one of these data points. So we have some vector y, and instead of trying to solve this specific equation, which in general is unsolvable, we can project y onto this subspace W. And we can solve that associated system, and then we'll say what that means in a moment. In fact, actually, we can say what it means right now. If we take the difference of these two vectors, y minus this projection, what are we minimizing? So an arbitrary vector in this subspace, let's write W as an arbitrary vector in this subspace, is a linear combination of these columns. So let's write that linear combination as M, suggestively, AE1, which is the first column of A, which is just all of these x data points, plus B times the second column of A. And we want to minimize the distance between our data set, our data vector y, with this vector. So in other words, if we take this difference, let's replace this with W for now, because let's imagine we don't yet know that this is the projection. So this difference is trying to minimize y minus m AE1 plus b AE2. And if we look at what each of these components give you, then this equals, let's square this, just so we don't have to deal with square roots. Then this is the sum. So first let's take an arbitrary ith component here. It's yi minus m times xi plus b. And that's it. And then we take the sum of these squares, because that's what this means, and we sum over all I from 1 to d. So we want to minimize this expression. In other words, we're taking our actual data set y, and we're taking this, which is our best fit curve, using our data set x. And so we're trying to minimize all of these distances. So these are actually the vertical distances between the best fit curve and this line. It's the vertical distances because this is saying our y data point minus the value of this line at that point. And we take that distance, that difference, which is this little vertical height, we square that height, and then we add up all of these heights. And we want to minimize that expression. So the solution to this least squares problem is graphically given by an expression like that. And we know how to solve this. To solve this, we apply our previous theorem. And we know that to solve this, we can solve instead A transpose A equals A transpose AX equals A transpose, and X is Xc. Let me write this as Xc, and A transpose Y. So this is the problem that we want to solve, and we want to solve this for Xc, and Xc is our vector of unknowns. So in order to do this, we have to write down what A is. We already know what A is. We have to write down its transpose. We have to multiply those two things. There's a lot of things we have to calculate. So let's do that on a fresh board space. So I've written the problem setup, and we have the matrix A with our data points for x and our vector y with y. And I've taken the transpose and I've written it on the left because we'll be applying matrix multiplication to this side to solve for A transpose A. And then we'll also matrix multiply A transpose with y. So if we multiply these two matrices, it's the first row here times the first, take the dot product with this column, and that's x1 squared plus x2 squared plus xd squared. So the first top left entry is the sum of the squares of these entries from 1 to d. And the second entry on the top is the first row times the second column of A, and that's x1 times 1 plus x2 times 1. In other words, we're just summing up all of the different x values. And on the bottom left, it's the second row here with the first column. That's the same as it was in the top right. And then the last entry on the bottom right is the second row with the second column. And that's 1 times 1 plus 1 times 1 plus 1 times 1, d times, which is just d itself. So this is A transpose A. And A transpose Y equals, first of all, notice that it's just a 2 by 2 matrix. So we're going to be solving a rather simple system. It's just a 2 by 2. So A transpose Y is now take the values of x, multiply them with the values of y. It's sum I equals 1 to d, xi with yi this time. And then it's the second row with this, and that's just the sum of the y's. And it's our vector with two components here. And we want to solve this system. Now, it's only a 2 by 2. So on the one hand, we could probably set this up as a row reduction, an augmented matrix problem, row reduce and isolate whatever we need to so that we can solve for this vector xc. On the other hand, it's only a 2 by 2 matrix, and row reduction might be a little bit complicated. For instance, we might want to maybe divide this entry by the sum of the squares of all of the entries, but maybe that's a problem if every single one of these is 0. It's a little bit tricky. So it's very convenient to first of all find out when this matrix is invertible, and if this matrix is invertible, we can multiply both sides by the inverse. So if A transpose A inverse exists, and we'll figure out what that means. We'll compute the determinant of this to determine when this inverse actually exists. Then we can solve this system pretty easily. and it's C, which is, again, remember, our vector of unknown coefficients m and b, then this equals A transpose A inverse times this vector right here, A transpose Y, which we've already computed. So, in terms of the setup, it's relatively straightforward. Maybe calculating this actual inverse might be a little bit of a challenge because of the arbitrariness, the generality that we're doing this in. So first, let's compute the determinant of this matrix. And that's just this times this minus this times this. Now, because we're multiplying these two sums, we really have to be careful about the indices. Remember, this is a sum of stuff multiplied by a sum of stuff. So we can't just say that this is sum xi squared. It's actually, there's a lot of foiling going on. And this is given by d, the sum of the squares. That's from the first term, this times this, minus this times this. And in order to make that calculation a little bit more straightforward, I'll rewrite one of the indices as a j instead of an I so that we don't get confused. So this is xi times xj. And each of these sums, there's actually two sums here, one for the index I and one for the index j, and they both go from 1 to d. So this is the determinant. And I won't do the rest of this calculation out, but this, I'll make a claim, and you should check this, that this equals 0 if and only if xi equals xj for all I and j. So the only time that this determinant vanishes if all of the xi data points happen to be equal to each other. Now, it takes a little bit of time to actually show that, but you can do it. And this is the only instance when this matrix is not invertible. And if you're thinking about data, this basically would mean that all of your data points lie along a vertical line. And then it makes sense that you can't find a function of the form y equals mx plus b to fit this, because the only line that'll work is a vertical line, and in that case the slope is infinite, so you won't find a solution. So it makes a lot of sense why this is the only case where that happens. Otherwise, if you have even a single point that's off of this line, you will be able to find some curve that best approximates this data. Although you would think that maybe if all of these points lie here and there's a data point way out here, then maybe this data point is, there's something wrong with it, or more investigation is needed. Such a point in this situation would be called an outlier. And I may discuss about this at some point, but that's not the focus of this specific video right now. So that's the claim. So this determinant vanishes if and only if all of these data points are equal. So let's assume that this does not happen. Assume there exists an I and a j that's not equal, an I and a j which they are not equal, and such that xi is different from xj. So we just need to assume that we have at least two data points that do not lie on, that are not the same. When we make this assumption, we can compute this inverse. And this is easy because it's just 2 by 2. We maybe remember this formula. We just divide by the determinant, we swap these two entries, and we negate these. So this is just 1 over this determinant, and I don't want to keep writing it, so let me just write determinant of A transpose A. And just remember that it equals this. And then we swap these entries, so this is D, and here we have sum. And there's lots of indices now, and I don't want to conflate any of these indices with each other, so I'm now going to call these k or something. So this is k equals 1 to d, and this is x k squared. And here we have minus sum xk. Oops, k goes from 1 to d. And this is minus k from 1 to d. And this here is the inverse of our matrix. And then what we have to do is we have to take this complicated expression and multiply it by this vector. And once we do that, we'll find out what the values of m and b are. So we'll need, again, a little bit more board space to do that. So here I've rewritten our problem, and remember we're trying to solve for the coefficients m and b for linear regression for an arbitrary data set. And we computed that A transpose A as a matrix equals 1 over the determinant of that matrix, which we found was D times, that's a D, times xi squared minus, let's use the indices I and j here, xi times xj. So this is 1 over the determinant times our matrix, which was, to not conflate these indices, let's call these indices k. This was, I believe, d here for the inverse. On the bottom right, we had sum of the squares, xk squared minus k xk. I'll stop writing from 1 to d. It's just getting a little bit annoying. Minus sum k xk. But I'll always write the subscript that we're summing over. So this is A transpose A inverse. Now A transpose Y, well, I can't remember if I wrote it, but if you remember what A transpose looks like, we computed A transpose Y. Yeah, now I remember. But the thing is that we'll have to be careful about indices, because I believe we use the indices I there as well. And we've already used I, we've already used J, we've already used K, so let me call them L. So this was sum XL, YL. L goes from 1 to D. And then on the bottom part of this two-component vector, it was just the sum of the y's. OK, so all of this mess is the left-hand side of this expression. Let's multiply these two matrices and see what we get. So let's just do that. Then we get, and let's keep this determinant factor here. And I'm writing all of this because you'll see that it relates to something you may have seen in a course on statistics or probability. So then we multiply d by this, and we multiply this by this. I'm just going to do this all out. D times this sum over, it's just L, one index, XL, YL, minus this expression. There's two sums here now, K and L, XK, YL. That's the first component of this vector. And the second component is this times this. Now we have a bunch of stuff going on here. Plus this times this. So let me write the plus on the left. This becomes sum over K and L, and xk squared, which we can write as xk, yeah, let's just write it xk squared, YL, minus xk. Now this is a little bit different, right, because we have two sums, K and L, and this time it's not xk squared, it's xk xl, YL. And this is what equals MB. Now, so this actually solves the whole problem. So we know that M equals this first expression here divided by this determinant, and the y-intercept equals this expression here divided by that determinant. Now, does it equal anything familiar? If we look at M itself, and we divide the numerator and the denominator by d, we get that M equals sum over L, XL, YL, minus 1 over d, sum K and L, XK, YL, divided by xi squared minus ij xi xj. Now, each of these expressions actually show up in statistics quite often, and they're actually given special names. We call let's do the denominator first, since this one's only involves a single data set. This is called the variance of the data set x, where x vector equals x1 through xd, and it's also written as var of x. And this just equals, by definition, the sum of the xi squares minus xij, xj. So that's what the variance is, by definition. And the covariance involves two data sets, our x's and our y's. So it's of x and y. And this is defined by, I think, people have different notation. I don't know what the notation is. I don't really care. But it's this expression on top. So this is sum L xl yl minus 1 over d. Oh, did I forget a 1 over d? I did. This should have a 1 over d here. Minus 1 over d. X, K, Y, L. That's an L subscript on that last Y. So we have that our linear regression problem actually derives for us the variance and the covariance of our data set. And we also have explicit expressions, if we wanted to, for the least squares solution if we want to fit data to a straight line curve. In the next video, we won't apply this general result because I don't think anybody would expect you to memorize something like this. Instead, we'll set up the problem in an explicit example, redo the whole procedure just so you get a feel for it with specific numbers involved, and how you would actually compute the inverse without all of these sums or anything like that if you're just given a relatively small data set. If you're given relatively large data sets, then you might want to go through this approach, or you might have to program something that does it for you. So let's actually do an explicit example using actual numbers. Here's a graph, and here's some data points. The x-axis is the horizontal axis, and the y-axis is the vertical one. And let's just use a unit grid so that the distance between any two of these grid lines has length 1. So the data that we're given, according to this plot, is we have our data vector, and we want to try to fit to a line of the form y equals mx plus b. So let's write down our matrix A. And our matrix A, remember, consists of all of the x's, if we write it in this form, and 1's all along the right column. So how many data points do we have? So what's D? 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. So you should have 7 entries in this column, in the columns of A. And let's go in order from left to right, filling in all of these entries. The order that you go in doesn't really matter as long as you're consistent with the corresponding values of y that you use. So in this case, the first value of x is at x equals -4, -3, -1, 0, 1, 3, 4. I've chosen it to be somewhat symmetric just for convenience of the computation. So it's -4, -3, -1, 0, and the x values, positive x values, are 1, 3, and 4. So this is the matrix A. And the vector y is the corresponding values of y. So for x equals -4, the value of y is at -1. Again, there are D entries here as well. The next one is 0. Then it's 1, 0, 1. And the last two are 2 and 4. So this is all of the information that we need. And if we compute A transpose A, what do we get? So I won't write out A transpose, just take the transpose of this. Then we know that we're taking the dot product of this vector with itself to get the top left entry here. So what's the dot product of this with itself? it's 4 squared times 2, so it's 16 times 2, which is 32. 9 plus 9, which is 18, so 32 plus 18, which is 50, plus 2. So it's 52 on the top left. The dot product of this with this is 0 because all the negatives cancel out all of the positive entries. Again, I chose that specifically so that this happens, so that computing the inverse is much easier. And we can immediately solve this system. Now, A transpose acting on Y, oh, sorry, the bottom entry is just D itself, and D is 7. Now, A transpose Y is this times this plus, so negative 4 times negative 1 plus negative 3 times 0 plus negative 1 times 1, and so on. So negative 4 with negative 1 gives you 4. That with 0 doesn't change anything, so we still have 4. Then that's negative 1 from 4, so that gives us 3 left over. This one brings it back up to 4. Then this 6 brings it up to 10. And this is 16, so we get 26 in the first entry. Maybe you have faster ways of doing this, I don't know. So then A transpose, if we take the second row here of A transpose, which is this column of 1s, and we dot it with this, these cancel, these add, so we get 7. Now solving this system is pretty straightforward. Right, this is 52007, and one side 26.7. We just have to divide everything by 50, the first row by 52, the second row by 7, and we immediately arrive at the vector MB. Our vector of unknowns is 1/2 and 1. So this tells us that the best fit approximation that minimizes the vertical distance squared between that line and all of these data points has slope 1/2 and y-intercept 1. So the line that we want to fit this to is 1/2 x plus 1. And if we try to sketch what that graph looks like, we know that it goes through 1, so let's include that point here. And it has slope 1/2, so when it gets to this, when it moves 2 units over, it moves 1 unit up. So here's the next data point. We connect these two with a straight line. And moving over 2 units to the right, 1 unit up, we connect that with a straight line, and we keep doing this. I mean, this is how I draw if I don't have a ruler or anything on hand. I would try to draw something like this. So this straight line here, if you notice, it happens to actually go through one of the data points. That might not happen, but as you can see, it doesn't go through most of them, but it's a pretty reasonable approximation to this data set. So this is how you would actually solve a least squares problem, specifically in the context of a fitting data to a linear curve, or rather an affine curve to be technically correct. This is how you would do it in such an example. In the next few videos, we're going to generalize the idea of linear regression just in terms of a straight line data fitting to linear regression in the sense that you can data fit your data to sort of any curve, almost any curve. And the way that we're going to do this is we're going to set up some notation, and we're going to let f1 through fk be linearly independent functions. And what I mean by this is it's the same definition of linear independence of vectors, namely that there does not exist a set of numbers a1 through ak such that when you sum up, so let me just say this, i.e. there does not exist a set of numbers a1 through ak, so these are real numbers, or complex if these are complex valued functions, such that the sum of ai fi equals 0 as a function. So let's just say the domain of our function is whatever we need to specify it to be. For example, the whole real line, or maybe an interval or something like that. So, and imagine you're given data points. And let's say the given data points, again, we're going to use our x and y variables. So your input is x and your output is y. And you have a whole list of data, x1, x2, up to xd, where d is the number of data points. And you want to fit these points to these functions. So in other words, your hope is to somehow fit y1 equals to a1 f1 of x1 plus dot 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 ak f k x1. And not only do you want this, but you also want this to hold for all of your data points. So up to yd a1 f1 xd now plus dot 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 a k f k x d. So this is your hope, but if d is much, much greater than k, then this is unlikely. It's usually impossible to find coefficients that fit all of these data. So before moving on, let's try to rewrite this expression in a linear way so that we can relate it to the linear regression problem we solved earlier. So set y to be this vector here. So let's call this the vector y. And what you notice here is that each of these numbers, so f1, x1 is a specific number, we're taking a linear combination of these numbers with coefficients coming from the a's. So this looks like the vector y1 down to yd. This is what this equation is represented by, a matrix whose entries are given by these values of f. So f1, x1 in the first column, and up to yd, the coefficient in front of a1 is f1, xd. And then this goes up to fk, still x1, so x1 is the first row, and down to fk, xd in the last row. And this matrix is applied to the vector of unknowns, a1 through ak. So this is again of the form y equals a, and let's call it c instead of x to not confuse ourselves with the variable x that we've used for our data. So in general, it's impossible to solve this. And the way that we would like to solve this is, again, a least squares solution. So a least squares solution, or approximation to this, is a actual solution to A transpose y equals A transpose A c. So just apply A transpose on the left on both sides. And this is generally what we're going to solve for, and this will be fitting our data to the set of functions defined by these. But there are a few restrictions that have to be made. For example, the first maybe obvious restriction, if you think about it, is that these coefficients should be independent. And independent in the sense that I can't take any one of these coefficients and sort of re-express it in terms of the others. I'm not talking about linear independence, I'm just talking about independence. So we assume the coefficients are independent. And this just means, i.e., there does not exist an I from 1 through k such that ai is determined by aj by all the other aj's. So let's just say the set of aj's, where j is now from 1, excluding I, so I wrote a little hat over that to exclude I, up to k. So in other words, in terms of all of the other coefficients. So we assume that they're independent. And this is sort of obvious, right? Because if you wanted to fit your data to these functions and you assume that these were all unknown coefficients and you wanted to find the best value for them, then if you suddenly did that arbitrarily, then it's unlikely that this relationship between them holds in that situation. So in general, we definitely want to make sure these coefficients are independent. Not only that, we also should assume that the functions are linearly independent. So we assume that these functions are independent as well. And this is because, so suppose that one of these actually depended on the other. So because if, let's say, fi equal to some linear combination of the other ones, so let's say bj, fj, so j goes from 1 to k, but j is not equal to I, so we're just saying, like, for these to be linearly independent, another way is saying that at least none of them can be expressed in terms of the other. So if that fails, at least one of them can be expressed in terms of the others. So because if for some numbers bj, then what happens to these expressions? So then if we take f and we take its linear combinations, so let's say ai, sorry, let me not use the index I, let me use the index j now. So let's take sum of aj, fj, and this breaks up into two parts now, right? Because we have a sum over j where j is not equal to I. So this is j not equal to I. And the sum goes from 1 to k. So this is aj, fj. But then we also have plus ai, fi. But this term equals this. So this equals sum over all j not equal to I. Another sum over all j that are not equal to I. So we have aj, I'm just copying this term, fj, plus ai times this. So ai times bj, fj. And then this is all in parentheses. And now you notice that fj is a common factor. So when you factor that out, you get sum j not equal to I. And then this is aj plus ai bj, fj. So now what we've done is we've re-expressed our linear combination of these functions, so the way everything that's on the right-hand side here in particular, and we've re-expressed it in terms of functions, in terms of k minus 1 functions. And now our coefficients have changed. So in other words, there was already a dependence on the coefficients in some sense, and so we usually demand that the functions are linearly independent so that we avoid this issue. In the next video, we'll explain more generally a simple situation that occurs in which this function, this linear system, is always solvable by the method that we used earlier, namely by taking A transpose A inverse. Let's now understand when we can solve A transpose Y equals A transpose A, C, using the method of taking the inverse of A transpose A. Now, in order to take the inverse of this, we know that we need to require that the kernel of this matrix, so by the way, if A is a D by K matrix, and again, D is typically much, much larger than K, then we want to know when this exists. So one of the situations when this exists is when the kernel of this matrix vanishes. That's one of the criteria. So 0 as a vector space. As a vector subspace Rk. So when does something like this happen? So to understand when we can apply this method, let's suppose that this is the matrix A. A goes from Rk. This is Rd here. And this here is the image of A. If we take the orthogonal complement of this image, in this case, unfortunately, I can only draw the orthogonal complement as having a single dimension, but you could imagine that it has a much, much larger dimension, especially if D is much, much larger than K. So the first claim that we'll prove is that the orthogonal complement of the image of A equals the kernel. Now, in order for this to make sense, I need to take the kernel of some matrix. Now, the image of A is in Rd. Its orthogonal complement is also in Rd. And I can't take the kernel of A because that wouldn't make sense. The kernel would live here. So I have to take, the only other thing I can take the kernel of is maybe the kernel of A transpose. So we'll do that. So we'll take the kernel of A transpose. And it turns out that these two are equal. So how do we see this? Let's visualize A as a matrix of vectors, so A1 through AK. And when we take the transpose, these columns just become the rows. So we'll do this proof just by showing that one is contained in the other, just to make it very explicit. So suppose that the vector v is, let's start with being an element in the orthogonal complement. So let's say v is perpendicular to A, the image of A. And then let's see if it's in the kernel of A transpose. So when we take A transpose applied to V, what do we get? So we'll write the matrix A transpose. Now we take these columns and turn them into rows. And we apply it to the vector V. But matrix multiplication tells us that when we do this, we take this row and multiply it by this vector. In other words, we take the dot product. So this equals another vector, and it's a vector in Rk. And what we get is A1 dot product with V as the first entry, all the way down to AK dot product with V. But if V is in the orthogonal complement of A, then it has to be that all of these dot products are 0. So this is actually the 0 vector. And therefore, this containment holds. The orthogonal complement of the image of A is in the kernel of A transpose. So that shows half of the theorem. Now let's suppose, so conversely, suppose that the vector u is in the kernel of A transpose. Then, by the same argument, being in the kernel of A transpose u equals 0. But A transpose u is A1 dot u, all the way down to AK dot u. But the 0 vector says that all of those are 0. And because the image of A is spanned by the vectors A1 through AK, we know automatically, by the same exact argument, that u is perpendicular to the image of A. So it's almost the same argument, which is why I'm not writing it. And therefore, this containment holds. And that's the other half of the theorem. So that's the proof that the kernel of A transpose equals the orthogonal complement of the image of A. Why is this useful? It's useful for the following very important reason. And it says that the kernel of A equals the kernel of A transpose A. You can already see why this is going to be useful, because instead of looking at the kernel of A transpose A, which we take two matrices, multiply them, it's going to be a little bit more difficult matrix to work with. If we could just look at the kernel of A, that would probably save us some time. So let's prove this. In one direction, it's pretty obvious, but I'll write it out anyway. So let's first prove the direction that the kernel of A is inside here. So let's prove this containment. So if U satisfies AU equals 0, then A transpose A U, because this thing is 0, also equals 0. So that direction is pretty straightforward. Let's look at the other containment. So suppose V satisfies A transpose AV equals 0. Then what this means is that AV is in the kernel of A transpose, i.e. AV is in the kernel of A transpose. But by the previous claim, the kernel of A transpose equals the image of A, taking the orthogonal complement of the image of A. So what's the picture here? Actually, let's go back right here. So we have that AV, which by the way is in this plane, also is contained in the orthogonal complement of that image. And the only vector that's contained both in A and in the orthogonal complement is the 0 vector. This implies that AV equals the 0 vector. In other words, V is in the kernel of A. And now the containment has been shown in both directions, and that's the conclusion of the proof. And let me just write out the final corollary, which is the useful one for us. It's like corollary 2, is that a least, so let's say A transpose, how do I say this? A transpose A inverse exists if and only if the kernel of A is trivial. So it's only the 0 vector. Now, why is this reasonable? So this isn't really an example. It's sort of an idea for why this is this usually occurs when you're trying to fit data. So our matrix A is typically going to be of the form F1 x1 dot 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 F xk Fk x1 all the way down to F1 xd Fk xd. So typically our matrix A looks something like this. And what would it mean for this to have trivial kernel? It would say that none of these, so all of these vectors are linearly, the set of these vectors, the column vectors, are linearly independent. Is that likely? So when might something like that happen? So for instance, if one of these functions did depend on the others in a linear way, so for instance, in the last video we said that we assumed that these functions were linearly independent. If they were dependent, what could happen? One of these column vectors could be expressed as a linear combination of the others. And therefore, these columns would be linearly dependent. And if these are dependent, then this has a non-trivial kernel. So that's at least a sufficient, that's at least one condition, that's a necessary condition for this to have a non-trivial kernel. So we demand that these functions are linearly independent. But furthermore, not only do we ask that these functions are linearly independent, but it also implies that these specific vectors, after we apply our data, are linearly independent. But if D is much, much, much larger than K, we only have very few of these vectors, right? So the number of entries is D, but we only have K vectors. So it's kind of easy. If you randomly chose, if you arbitrarily and randomly chose K vectors in a very large dimensional space, randomly, with almost almost surely it will be that those vectors are linearly independent. Think about it. Just choose random numbers. So for example, let's write pi e 1, 2, square root of 3, 3, and the vector 1, 1, 1. I'm pretty sure that these three vectors are linearly independent in R3, and I randomly chose them. So even if d is not drastically larger than k, but even if it's just greater than k, almost surely you'll pick linearly independent vectors. So if your data is sufficiently, distributed well and it's not lying exactly on one line or something like that, then chances are these vectors are linearly independent. So that's where it's going to be useful. And in the next video, we'll actually apply this to a simple example that you probably don't need a calculator to compute with. In the next few videos, we're going to be working with arithmetic modular 2. So we're going to deal with all even numbers are equal to 0, and all odd numbers are equal to 1. So for instance, 2 times 3 is 6, which is an even number, so it's 0. And 7 plus 3 is 10, which is also even, which is 0. For another example is negative 3 equals 1 in this case. So anytime we do arithmetic, for the most part, when we add, we're only going to be caring about the parity of that number. And this is going to be, there are multiple reasons for this, one of which is simplicity, the other of which is that it's related to computer science. So we're going to let z mod 2 be exactly those numbers, and with the arithmetic that I just said. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 2, which is 0, and then multiplication similarly. 0 times 1 is 0, and 1 times 1 is 1. And we'll also work with vectors whose entries are elements of z mod 2. So these are going to be vectors of the form x1 all the way up to xn, where x1 through xn are in z mod 2. And we can also do arithmetic the way we usually do with vectors of this sort, by just adding component-wise and scalar multiplication on each components as well. The interesting thing about this vector space is that unlike the vector space R to the n, this has finitely many vectors. So how many vectors does this vector space have? Well, first of all, here there are 2 elements. And if you have n component vectors, think how many entries, think what possibilities you can put in that first entry. You can either put a 0 or a 1. And as soon as you move to the next entry, you can also put a 0 or a 1. And therefore, each time you go through these entries, you have 2 to the n total possibilities. So the number of vectors in z mod 2 to the n is 2 to the n. And one of those vectors is very special, namely the 0 vector. And the non-zero vectors, well, there's just one less of them. And I know that sounds like a trivial thing to point out, but it'll actually be important in our discussion. And so for example, this is the main example that we'll be working with. Z mod 2 to the 3rd power has 7 non-zero vectors, for example. So let's make a definition first. First, we're going to be exploring a lot of mathematical curiosities, and then we'll see how they apply to an actual physical situation. And I'd rather you have a little bit of suspense before we get there. So first, we're going to do some math, and then we'll talk about the applications. So a Hamming matrix is a matrix H with k rows and the columns of H consist of all the non-zero vectors in Z mod 2 to the kth power. So k here is a non-negative integer. In fact, let's just, suppose it's a positive integer. So for example, when k is 3, we have 7 non-zero vectors. And what this is telling us, all right, now let's try to understand these two matrices a little bit more, the matrices M and H that we introduced earlier. So recall that H was the matrix, it was the identity matrix, a 3 by 3 in this case, and another matrix Q, and M was Q, and then the identity 4 by 4 matrix. And both of these numbers can be generalized as long as it's an appropriate size, and it satisfies the requirements that we made earlier, namely that H consists of all of the non-zero vectors in the vector space z mod 2 to the power, where that power is determined by the number of rows here. So given the setup, let's introduce a little bit more notation. And that notation is going to be, we're going to define these, that subspace, which was the kernel of H and also the image of M. So let's call these image of M, which is also the kernel of M, kernel of H rather. Let's denote this by C. So for the rest of these videos, C will refer to exactly that subspace. Now remember, this is a 4-dimensional subspace inside of z mod 2 to the 7th. Okay, we're also going to introduce other notation. Let C subscript I be that subspace shifted by the ith unit vector in z mod 2. So it's going to be C plus EI. And this just means, by definition, the set of all vectors of the form V plus EI, where V is in C. Now this is not a subspace, right? Because we can't add two vectors and stay within the subspace, stay within this subset. But at the very least, you can think of this as the subspace shifted by some vector. And we can define this for all I between 1 and 7. Because that's how many non-zero vectors there are in, that gives us a basis of vectors in z mod 2 to the 7th power. And now let's write some additional facts regarding these subsets. So the first thing is that we already know that C is the solution set of a homogeneous system. Namely, it's the kernel of H. Ci is also the solution set of some system, though it's no longer homogeneous. Ci is the solution set of the inhomogeneous system Hx equals Hei, where this whole thing, Hei, is the ith column of H. Secondly, if we take any two of these different subsets, Ci and Cj, then Ci intersect Cj. So if we look at all of the vectors that are common to both of them, it turns out there are none. So it's the empty set for all I not equal to j. Third, each of these subsets are also disjoint from the solution set of the homogeneous system. So C intersect Ci is also empty for all I. And finally, and this is maybe the most interesting part of it, is that the entire vector space of all vectors is the union of every single one of these. So it's the solution set of the homogeneous system with all of these other inhomogeneous solution sets. And because these are all disjoint, this is a disjoint union. So every vector in Z mod 2 is in exactly one of these subsets. It's either a solution set of the homogeneous system, or it's in one of these solution sets of the different inhomogeneous systems. So this is a very important claim. So let's actually prove it. So the first claim, now when we solve inhomogeneous systems, all we have to do is find one particular solution, and if we find that a solution exists, then the solution set of the inhomogeneous system is that particular solution plus the homogeneous solution that we obtained from solving, well, for the kernel of H. So notice, however, that we can just take x to b ei to get a solution set. So ei is a particular solution. And therefore, the solution set of the whole system of hx equals hei is that particular solution plus the homogeneous one. And that's exactly what the claim is. Ci is the solution set of this. Now, let's look at the second claim. The second claim says that these are all different. All of these subsets for different I and j have no common intersection. So, in order to prove that, let's pick two vectors, one in Ci, one in Cj, and they're going to be arbitrary. And then we're going to show that the only way that they can be equal to each other is if those subscripts are equal, if I and j are equal. So let's start, suppose that we have two vectors. Now, because we're a solution set of the homogeneous system, the kernel of H, and the kernel of H equals the image of H, our vectors are going to have this form. So suppose m u1 plus ei, so this is our vector in Ci, equals m u2, because we don't know if, right, these two could have different, they have come from different vectors, plus ej. So suppose we have these two vectors, and this one is in Ci, this one is in Cj. Now, if we apply h to these vectors, so let me just write that this is in Ci, this is in Cj, so we're totally clear. Now, apply h to this equality. What happens? Well, because these functions are linear, and we apply h to both on the left-hand side, this becomes h m u1 plus h ei equals h m u2 plus h e j, right? And hm of u1 is 0 because hm is the zero matrix. So this is 0, that's 0, and we're left with hei equals hej. Now the only way that this is possible is if I and j are both equal to each other, and the reason is because h, by definition, is the set of all non-zero vectors in z mod 2 to the third power, and they never repeat. So we only use those vectors once and only once. So to better understand this application, let's first notice that if we apply m acting on any vector u, the vector we get is q applied to u in the top part of that entries of that vector, and we retain a copy of u in the bottom. This is because the matrix M was q on top and then the identity matrix on bottom. So this is true for all u in z mod 2 to the fourth. And so a copy of your original vector sits inside of this vector. So imagine you're trying to send a message u across some sort of a channel, a communication channel, and you want a receiver to obtain that message. And you would like it for them to obtain exactly the message you sent, because if you hear something else on the other end of that line, or you see something else, then you may misinterpret what the sender is trying to tell you. So there's a sender and a receiver. And so, for example, during this transmission, there could be some noise, or maybe something that alters that message. You hear this all the time when you're on the phone, and sometimes the signal isn't working too well. You might not hear exactly what the other person is saying, or you might hear something a little bit different. So there may be disturbance along such a line. So for example, if we were sending, let's say, my name across this channel, and at the other end of the line, the receiver sees the word Archer, for example. Now, what was the original message that was supposed to be sent? In this context, you know the English language, so you know that there may be a specific word that this is corresponding to. But in this example, you have two possibilities that this word could be, at least. One of them could be Archer, or maybe Arthur. And in order for the receiver to verify what the message was, or one way to verify what the message is they could send that same message back and then basically ask, is this the message you intended to send? Okay, so now imagine that this person sends, let's say this person sends Archer back. And imagine another error occurs. And imagine that the error occurs, takes place, let's say, in the first entry. And it becomes Archer. And then the person is like, wait, did you want to send me the word Archer? Like, what are you doing with this message? Are you trying to tell me Escher or Archer? And so this person's going to send another message back asking, and you can see that this could keep happening for a very long time. So it would be very convenient to either this person can send multiple copies of that message, and then with lower and lower probability, the more messages you send, the more likely it is that the person on the other end will figure out what that message is supposed to say. So that's one option. But this option seems to take up a lot of resources, right? Sending a message over and over and over again is sort of multiplying the number of resources you need by the number of times you send that message. It would be very convenient if you could somehow have a scheme where the sender is sending a message and the receiver can apply a certain method that both the receiver and sender have agreed upon in advance to possibly identify if an error occurred and where an error occurred during that transmission. So that's what we're going to do. And we're going to simplify the problem by not looking at the English language. We're going to look at vectors whose entries are just zeros and ones, the simplest possible language that we can come up with, or at least the simplest the simplest alphabet we can come up with, an alphabet containing two symbols. So let's say we initially send the vector 0, 1, 1, 0 across this channel. Now, once this channel goes, I should have written it from right to left as I've been doing so, but let's go counter to this. Now, if one error occurs, suppose one error occurred, that means that error is going to occur in one of these four entries. And if it occurs in the first entry, the only possible thing that that 0 could become, because our language only has two symbols, is 1. So one possibility is that we get 1, 1, 1, 0 at the other end of the line. Another possibility is if the error occurs in the second entry, in which case we would have 0, 0, 1, 0, and so on. So in the third entry, 0, 1, 0, 0, and in the last entry, 0, 1, 1, 1. So these are the possible outcomes if we have exactly one error. Of course, if no error occurs, then the receiver will see the original message. But how do they even know that an error didn't occur or not? So the way that we're going to solve this problem is by using the previous situation that we had developed. We can take our original message, encode it in some larger message, and then this message is going to be contained in the subspace C. So if we send a message U, it's going to be contained in that subspace C. And if we send that message across the channel instead, what could happen to it? So initially, the sender is sending the message U is contained in the bottom part, but now mu is contained in z mod 2 to the 7th power. So it seems like a more complicated vector, but the only real messages that could have been sent, the ones that have no errors, are exactly in that subspace C. Any other vector in this vector space is not a message that the sender could have sent, because they're only working with images, the image of the transformation associated to M. So this message is going through. Now imagine that an error occurs somewhere along the way, error. And the message becomes mu plus. Now there are 7 entries in the vector mu, so there are now 7 possible errors that could occur. And these errors are exactly quantified by adding the unit vector in the ith row or entry of that vector. So this error occurs. But the reader on the other end is going to see this vector v. They don't know that it is a priori this sort of combination. All they see is some vector of zeros and ones. But they can use h to identify what form the vector v is in. Remember we said that if h of v equals 0, then this implies that the vector v is in the subspace C, which is the image of M. And if h of v equals a non-zero vector, then that non-zero vector is one of the columns of h. This tells us that v is in Ci. But remember what Ci was? It was this subspace plus the unit vector ei. So it tells us that if a receiver receives the vector v and they apply h to it, they can identify which of these subsets it's in. And if the vector that they see after they apply h is 0, that tells us that no error occurred. So we're going to assume at most, one error occurs during the transmission. And if we make that assumption, then these two applications, an application of h to v, will tell us where an error occurred. And if we've identified where the error occurs, right, this says that if we see that the h of v is hei, then we know that the vector is of this form, and how do we fix it? So if it's, let's say this is case 1 and this is case 2, in case 1, how would the receiver identify what the original message is? They would look at the last 4 entries of the vector v, because that's where u is, and we know that no error occurred. So the original message sent by the sender is the vector corresponding to the last 4 entries. Of the vector v. And in the second case, what happens then? Well, if in the second case we found that h of v equals h of vi, then an error occurred in the ith entry of v. And how would we fix that? Well, we would just subtract ei, but subtracting and addition are the same in z mod 2. So to fix, we know that the original message will be v plus ei. Well, not the original message, but what the receiver sent after applying the transformation M. And when they do this, then they can read off the last 4 entries of this vector. The last meaning the bottom 4 of this vector, v plus ei, is the original message. So let's just do this in an example just to see how exactly this works. So imagine you're the receiver and you see the vector v equals 0, 0, 1, 1, 0, 1, 1. If you apply h to this vector, so I'll write h to remind you, because otherwise, how are we going to do this computation, huh? So this is 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. And then we apply the vector v here. And if we apply matrix operations here, we will get the vector 3, 2, 3. But 3 is 1 in z mod 2, and 2 is 0, so this becomes 1, 0, 1. So we take this vector and look where it appears in this matrix. And in this case, it is the 6th column of H. This means that an error occurred in the 6th entry of this vector here. So error in 6th entry of v. And therefore, if we alter the 6th entry, that would mean we change this 1, the second last one, to a 0. So that means the original message is 1, 0, 0, 1. Because we take the last 4 entries of this vector, and then we switch the 6th entry. If we had found that the second entry was an error occurred in the second entry, we would have changed that 0 to a 1 and left the original message here, and that would have been the message that was sent by the sender. So that's the basic idea of how this works. And again, we worked with a case where we were dealing with sending messages of length 4, and we used a larger vector space to encode the possibilities of computing those errors. And you could also do it by using by having H to be a matrix consisting of all the non-zero vectors in z mod 2 to the k. It will allow us to encode a message of length given by the number of columns in that matrix Q, and we already calculated that the number of columns in that matrix Q is 2 to the k minus 1 because of the 0 vector, minus an additional k from the k vectors we used on the left-hand side of the matrix H. So we can encode quite a large number of messages under the assumption that at most one error occurs during transmission. So let's now analyze in a little bit more detail what is QU actually doing. So we know that that matrix M that we had, it was broken up into 2 parts. And when we send a message U across a channel, we will keep our original message in one part of that vector, but we'll add a bunch of fluff to it. And what is the meaning of that fluff from maybe a different perspective? It turns out that there's a very interesting sort of logical thing that's going on between the entries of U and what Q is doing to those entries. And the idea is that it's adding those entries in such a way as to maintain the sort of consistency. So if we take actually QU and we apply that matrix Q that was left over, the vector we would get in terms of the entries of U, so U is going to be U1 through U4, the entries of this vector are going to be U1 plus U3 plus U4, U1 plus U2 plus U4, and the third entry, because this is a 3 by 4 matrix, is going to be U1 plus U2 plus U3. And these entries here are called, well, let's call them P1, P2, and P3 for now, and they are called parity bits. And the reason they're called parity bits is because when this message gets sent across a channel, if an error occurs, these entries are summing up the entries of the vector u in some specific way. And if an error occurred, right, we have some vector p1, p2, p3, and then u1, u2, u3, and u4. If an error occurred in one of these entries, then these parity bits will detect if an error occurred and where the error occurred based on the consistency of this formula. So let's see how this works in an explicit example. Let's say we have the vector 0, 0, 1. And I'll break this up into the two different parts so that we isolate the parity bits versus the original message. And by the way, this isn't the original message that I'm writing right now. This is what happens after it's sent. And let's say the receiver sees this message. I believe this may be the example we were working with a moment ago. So let's now look at these formulas and see what they say. So P1 on the one hand equals 0. But let's see if the sum of these entries is also equal to 0. So if we take u1 plus u3 plus u4, we get 1 plus 1 plus 1 is 3, which is 1, which is not equal to 1, which equals u1 plus u3 plus u4. What does this mean? This means an error occurred in one of these entries. And when I say one of these entries, I mean either P1, U1, U3, or U4. So let's write that down. P1, U1, U3, or U4. And we know it has to be exactly one because, again, we're assuming at most one error occurred. And because of this inconsistency, we're guaranteed that an error occurred. The only way no error would occur is if all of these would be consistent. So if P1 does equal this, if P2 does equal that, if P3 does equal that, because this would say that our vector is of this form, m applied to the original vector u. So that doesn't exactly tell us which of the errors it is yet. Is it P1, U1, U3, or U4? So for that, we'll look at the other parity bits. So let's look at P2. The vector we see says P2 is 0. Is that consistent with this formula, U1 plus U2 plus U4? So U1 plus U2 plus U4 is 0. So that actually is consistent. What does this tell us? This tells us that no error occurred in any of these entries. Because if one error occurred, it is impossible for these two to be equal to each other. So this means P2, U1, U2, and U4 are all error-free. Now let's compare this to the first one that we analyzed. The first one said it was possible that the error occurred at U1, and it was also possible that the error occurred at U4. This new observation tells us those two possibilities, it's not possible that an error occurred in those entries. So now the only possibilities left are P1 and maybe U3. So we'll keep that in mind when we go to the last parity bit, which will then isolate exactly where the error occurred. So P3 is equal to, well, from this it's 1. And is that equal to U1 plus U2 plus U3? U1 plus U2 plus U3, it's equal to 0. So that's not equal to this, which is U1 plus U2 plus U3. Now this tells us that error is in one of P3, U1, U2, or U3. We already know that U1 and U2 are not possible, right? U1 and U4 are not possible. And the only error that's common to both of these, right? Because we know one error occurred in either P1 or U3, or it's possible that an error occurred in P3 or U3. But if it was P3, right, suppose that the error occurred in P3, then this would have been fine. It would have been unaltered because we wouldn't have detected an error. U3 would have also been OK. So the only possibility in this case is that an error occurred in U3, the one that's singled out from these three parity bits. So error in U3. And therefore, if we go to this original message, the message that we received, rather, and then this is the message we received, what we would have to alter is the U3 entry of this to get back the original message. Therefore, the original message is the last four entries as it was before, but now we alter that third message, that third entry, to get 1001 as the original message being sent. And this is consistent, I believe, with the answer that we obtained earlier. So you might be wondering, okay, this is a little bit more intuitive because we're sort of counting up our different entries in different ways and sort of using a process of elimination method to isolate exactly where the error occurred. Now, of course, that is a little bit more straightforward. It's easier to work with. It's easier to think about the first time you see it, perhaps. On the other hand, the linear algebra method, it allows you to see it from a maybe potentially different perspective. And I would think that if you're working with a much, much larger message, that the linear algebra method seems to be a lot easier to work with, especially when you look at the way that we multiply those matrices. And the form of the Hamming matrix that we constructed, so let me just say this, that the CS Hamming matrix looks a little bit different. For instance, I think it starts out with 1, 0, 0, 0, 1, 0, but then the third column is not 0, 0, 1. I think the fourth column is 0, 0, 1, and these other four columns are some permutation of the leftover columns I had. And now you can see if you were to manipulate this with the other matrix M that's associated to this one by demanding that the kernel of H equals the image of that matrix M, the algebra would be a little bit more. We can't just break this up into two blocks, identity and the leftover part. Instead, it has sort of this interpretation, but I believe the linear algebra calculations are much, much simpler if you work with a block matrix of the form that I indicated earlier. Now, this may change if you try to look at what happens if multiple errors occur. How would you potentially correct for all of those additional errors? And I'll leave you to think about that and to check out the literature. In the next few videos, we're going to compute the square root of a positive matrix. And the way we're going to do this is by introducing something called the functional calculus. And in fact, we'll learn how to compute, given any function under suitable conditions, what it means to apply that function to a given square matrix. So let me go ahead and state the statement of the theorem that we'll prove. And we'll prove this theorem first by doing an example, and then we'll prove the general result from scratch. So it says, let A be a diagonalizable n by n matrix and let F be a function, be a complex valued function, let's say, defined on what I'm going to call sigma of A. And sigma of A is the set of all eigenvalues of A. Now, if we have this set up, we can already define what f of A is, so let's do that. So f of A is going to be defined as P f of D P inverse, where P is the n by n matrix, is a matrix of eigenvectors of A written as columns, and D is the corresponding matrix of eigenvalues. And what do I mean by f of D? And f of D is defined to be, now D is a diagonal matrix, so let me just write out exactly what we're doing. If we have a matrix of eigenvalues, and these eigenvalues can repeat, so let me just write all n of them, and then this is 0 everywhere else. We define f of this matrix to be f applied to the elements along the diagonal and 0 everywhere else. So this is f of lambda 1, f of lambda n, and 0 everywhere else. So far, all we've done is set up our assumptions. So we have a matrix, we have the eigenvalues, we can define f applied to A, provided that we have a complex valued function defined on the set of eigenvalues. And here's the statement of the theorem. Then, there exists a polynomial Q such that Q of A, now what do I mean by Q of A? Q is a polynomial, and it makes sense to multiply matrices. So we can take A, we can square it, we can cube it, we can also take it to the 0th power, that's just the identity matrix. And then we can also multiply these by coefficients. So if I have any polynomial, it's very easy to define what Q of A is. You just write your polynomial, and where you have your variable, you replace it with the matrix A. So this is some polynomial in A, but it turns out to equal f of A as defined previously by this method of breaking a matrix up into its eigenvalues and getting its eigenvectors and constructing it this way. So that's what the statement of this theorem is, and it's very surprising because in general you can think of a very strange function such as the square root, and this is telling you that there is a way to write the square root of that given matrix in terms of a single polynomial. And what we're going to do first is do this through a simple example and illustrate it with that simple 2 by 2 matrix, and then we'll prove the general theorem. So we might as well start this example now and continue it in the next video. So the example is going to be, let A equal 10, 6, 6, 10. And our goal is to compute the square root of A. So the first step is find the eigenvalues. So another thing that we'll do is we'll review how to do these things. So to find the eigenvalues, compute the determinant of 10 minus lambda, 6, 6, 10 minus lambda. And this equals 100 plus lambda squared minus 20 lambda minus 36. And some of this simplifies. We get lambda squared minus 20 lambda plus 64. And this also factors into lambda minus 4 and lambda minus 16. So we know what our two eigenvalues are. They are 4 and 16. And while we wait for the next video, you can try to compute the corresponding eigenvectors, and I'll just give you the answer there in a moment. So here's the matrix that we're looking at, the associated eigenvalues that we found before, and corresponding eigenvectors, which you should have found by computing the corresponding eigenvectors. And so now let's compute what f, and f meaning the square root of A. So what is f of the diagonal matrix D associated to these eigenvalues? This is taking the square root of each of the corresponding entries on the diagonal. So it's just 2 and 4. And the matrix P is writing down these two eigenvectors. So it's just 1, negative 1, 1, 1. Its corresponding inverse is, the determinant here is 2. So it's 1/2. And then the rest of this matrix, we swap and we negate. So that's the corresponding inverse of this matrix. So what happens when we compute P f of D, P inverse? Supposedly, we should get the square root of our matrix, which means that if we square it, then we get back our matrix A. So if we multiply some of these out, I'll skip some of the steps. So if we take 1/2, when we multiply P with f of D, we get 2, 4, negative 2, 4. And then we also have P inverse still here. I've already pulled that 1/2 out. And multiplying these matrices out, we get, well, that distributes out, so we can just have 1, 2, negative 1, 2. And when we multiply those, we get 3, 1, 1, 3. So let's check that if we square this matrix, so let's just call this f of A. This is the definition that we gave of f of A. So what happens when we square this matrix? F of A squared, we get exactly 10, 6, 6, 10. So we do get our original matrix back. So this is one way of computing the square root of a matrix, or at least if it has positive eigenvalues, by computing the corresponding eigenvectors and eigenvalues. And supposedly we have another way of doing this. And the interesting thing about the following method is that we will not need to use the corresponding eigenvectors. All we need to use are the corresponding eigenvalues. And we'll find that polynomial that allows us to compute the square root of this matrix. So how do we do that? For the time being, what we'll first do is we'll find a polynomial Q such that Q of lambda 1 equals the square root of lambda 1, or f of lambda 1, and Q of lambda 2 equals f of lambda 2. So in this case, these are the square roots, and we already know exactly what their values are. This is 2, and this is 4. So what we're trying to do at this point, now we're doing a different problem, it seems like, because now we're just trying to find a polynomial that interpolates these two values of a function. So what we're trying to do is, so here's lambda 1, here's lambda 2, and we have a function which is just the square root, and we know that f applied to lambda 1 is 2, and f of lambda 2 is 4. Now this is not drawn to scale in any way, but what we're trying to do is find a polynomial that goes through these 2 points. Now you know that 2 points determine a line, so a straight line goes through these 2 points. And that straight line is of the form y equals mx plus b. So our goal is to find out what are m and what are b such that when we plug in x, which is our values of lambda, we get the corresponding values of y. So this isn't a very difficult problem, but what we're going to do is set it up as a linear algebra problem, even though you could probably immediately solve for m and b. And the reason we'll do that will be made more apparent later when we try to compute f of matrices of larger sizes where it will be more difficult to do the simpler method, and it's more reasonable to solve that system of linear equations using techniques of linear algebra. So when we set this up, we write on this side, since this is our y, we have m lambda 1 plus b, and this equals m of lambda 2 plus b. And our unknowns are m and b. So if we set up our matrix system, we get, and what I'll do for convenience is I'll put the 1s on the left. So I'll put my b's on the left column. So it's really b plus mx. 1, 1, and then this is lambda 1, lambda 2, and our two corresponding values, f of lambda 1, which in this case is 2, and 4. And we know what lambda 1 and lambda 2 are. They are 4 and 16. So really this is equal to 1, 4, 1, 16, 2, 4. And if we try to row reduce this system and solve it, what we end up getting is b equals 4/3 and m equals 1/6. So this line is of the form y equals 4/3 plus 1/6 x. And that's our polynomial. This is our q of x. And what we'll do in the next video is we will actually apply this polynomial to our matrix and see if it also satisfies the same equation. So here's the polynomial that we found as a real valued function in this case. And if we wanted to define Q of any matrix, I'm just going to write A, but it's for any matrix A, the associated polynomial on matrices would be 4/3 times the identity matrix, which in this case is an n by n matrix. Well, in this case it's 2 by 2 matrix, plus 1/6 A. So let's see what happens when we actually compute this. So we have 4/3 of the identity, both along the diagonal, plus 1/6 of our matrix A, so it's 10/6, which is 5/3, 1, 1, 5/3. And if we add these two matrices, what do we get? 9/3, which is 3, 1, 1, 3, which is exactly what we found for f of A before. So we already know that when we square this matrix, we get exactly our matrix A back. Now let's look at the more general situation. So we're going to go back to our setup where we have an n by n matrix A, a function f on the set of eigenvalues. So we write if A is n by n, and lambda 1 through lambda n are the eigenvalues, and f is a function on the set of eigenvalues to, let's say, the complex numbers, we're going to find a polynomial q that first satisfies the initial equation we wrote down for the associated eigenvalues. So our goal is to find a polynomial q such that q of, when we plug in our corresponding eigenvalues, we get f applied to those corresponding eigenvalues. And we already know that that problem will help us solve this one by a similar analysis. That's why we're reducing our problem to finding a polynomial on just a finite set of numbers rather than trying to find the answer to our matrix problem. And in fact, when we look at the degree of this polynomial, we notice that it was also matching the degree of the size of our matrix. And that's going to be true in general. We'll be able to find a polynomial whose degree is at most the size of the matrix that will solve that problem, namely q of A equals f of A. And why that happens is precisely because of this equation. Because there are going to be, at most, n distinct eigenvalues. And so we only need to find a polynomial. So let me draw this as visually. Let's just assume everything is real, so it's simple to draw this. So if we have lambda 1 here, lambda 3 here, lambda 2, maybe another lambda 4 somewhere out here. And let's say lambda 2 equals lambda 5, for instance. And if we apply f to these numbers, let's say they look something like this. What we're going to try to do is find a polynomial that fits through these, in this case, 4 points. And the reason it's 4 is because 2 of our eigenvalues are repeated. And so we have to find a polynomial through these 4 points. So, and if we had n distinct eigenvalues, we would have n distinct points through which we would have to find a polynomial. Sorry, I misspoke. I think I said degree 2. I meant degree 1 because 1 is the highest power, but it starts from 0. So in this case, we would find a degree 3 polynomial. And in general, it would be at most n minus 1 degree. So, and again, if we have multiplicity that's bigger than 1, then the problem is going to be a little bit easier to solve because we can find a polynomial of a lower degree. So let's just assume that all eigenvalues are distinct. It's not actually making our problem easier, it's making it a little bit harder, because if some of them repeat, then the problem is reduced to a smaller and simpler matrix algebra problem. So if we assume all the eigenvalues are distinct, we're really doing the hardest case. Now, when such a thing happens, we can write our polynomial q of x as a0 plus a1x plus a2x squared, all the way up to the highest degree, which, just by looking at the pictures, we're assuming it's of the form a n minus 1 x to the n minus 1. And if we write down all of these different equations, we're going to get another linear system. And the unknowns of that linear system are these a's. And we know the values of x's. Those are our different eigenvalues. And we know what the q of those x's are. It's f applied to those values. So the associated linear system that we get looks like ones along the vertical on the left side, corresponding to the coefficient in front of a0. The coefficients in front of a1 are the different eigenvalues. The coefficients in front of x squared are the squares of our eigenvalues. And then the coefficients in front of our highest degree are our eigenvalues to the power of that highest degree. And the augmented side of our matrix is the value of those different eigenvalues. So our goal will be to try to solve this system. Well, actually, our goal is a little bit easier than that. The statement of the theorem says that there exists a polynomial q that satisfies the equation q of a equals f of a. And so all we really have to do is show that such a polynomial exists. So we don't have to solve this. Solving it is what is q. So given a matrix A, what is a polynomial q? We're just trying to show that one exists. In other words, what we want to do is answer the question, does a solution to this system exist? And if we want to know a solution exists if Well, if we can solve this system, right, and one criteria that allows us to solve this system is that if this matrix here, which is an n by an n minus, what is this? An n by n matrix, right? It's an n by n matrix, and if this matrix is invertible. And when is a matrix invertible? If the determinant of this matrix is non-zero. So solution exists if the determinant of this matrix, which is called a van der Waals matrix, if this determinant is non-zero. So what we're going to do is, it's going to be a little bit of a brute force method, but we will find one way to compute the determinant of this matrix, and therefore show whether or not it's zero, and see if we can answer our problem. Whenever we have a problem with arbitrary n, it's a little bit difficult to see what the pattern is without doing an example. So I think it's good to try out a simple example, or at least somewhat simpler, by computing the determinant of the same matrix, but where n equals, let's say, 3. So we have a 3 by 3, and we want to compute this determinant. And we want to compute it in such a way so that we can use some of the ideas for computing this determinant and abstract it to that more general case. Now, this isn't the most simplest way to do such a thing, but it's one way, and I'm sure there are many, many other ways to compute this determinant, some of which may be certainly more clever than the approach that we'll take. So we're going to do this by essentially row reduction. And for the first step, we're going to get rid of the ones underneath the top left one, and by just subtracting the first row from those. So if we do that, that doesn't change the determinant, and we get the top row is left alone, and then the rows below it look like 0, 0, lambda 2 minus 1, lambda 3 minus 1, and this becomes lambda 3 cubed minus lambda 1 cubed, squared, and lambda 2 squared minus lambda 1 squared. Now, when we, lambda 2 minus lambda 1 is actually a common factor in this second row, because this becomes lambda 2 plus lambda 1 when we pull that out, and this is lambda 3 plus lambda 1. So when we distribute out, we get lambda 2 minus lambda 1, lambda 3 minus lambda 1, times the determinant of what's left over, which is 1, lambda 1 squared, 0, 1, 0, 1, lambda 1 plus lambda 2, lambda 1 plus lambda 3. And this happened because the determinant, remember, when you take the determinant and you multiply any row or any column by a number, you can distribute out that one number for that one column in this determinant. You can think of the volume. If you scale one side of the room by a factor and another side of the room by a different factor, then the determinant is computing the area, and you scale by both of those. But for each side, you only distribute one of them. So now, we're looking at this, and we want to compute the determinant of this. Now, of course, what's left over is a 2 by 2, so it's very easy to compute the determinant. But if we wanted to have an inductive proof, if we did a similar calculation here for a larger matrix, what we would have is lambda 1 through lambda 1 to the n minus first power up here, and then we'd have a much larger matrix, which isn't very easy to compute the determinant of by some explicit formula. It's sort of complicated to write. So what we want to do is we want to think of how to compute this maybe more conceptually. And what we can do is, notice that lambda 1 appears here in each of these two terms. And if we multiply the second column by lambda 1 and subtract, what happens is this cancels, the lambda 1 cancels, the lambda 1 cancels, and you're only left with lambda 2 and lambda 3. And you also don't change the determinant because you're taking one column and adding it to another. So this is also equal to the determinant of what's left over after you do that subtraction. This is 0, 0, 1, 0, 1, and then just lambda 2 and lambda 3 left over. Well, you can even do something even a little bit more simpler now. Now you have a 1 here. You can multiply this by lambda 1 to get rid of that. So I'm not even going to write that whole step out. We can just erase this and put a 0 here. And now, here's the amazing part. What's left over after you perform these operations is another Vandermonde matrix on the bottom right corner. And we can continue this process now, because the determinant of this, because this is a 1, is equal to the determinant of this. So we've reduced our problem from an n by n matrix to an n minus 1 by n minus 1 matrix of the same form. And if we keep going down further, up until maybe this step, or even further than that, then we would find out what the determinant of this matrix is. So if we did that procedure again, of course you can compute the determinant of a 2 by 2, no problem. But if you did that procedure again, subtract, you get a 0 here, move that over, you end up getting lambda 2 minus lambda 3. It's already it already breaks up like that pretty easily. And you get lambda 2 minus lambda 3, that pops out. So what you end up getting is the product of I and j. Let's say I is less than j, and j is less than or equal to 3, and I is greater than or equal to 1, of lambda j minus lambda I. So you actually get the product of the differences of all of these different eigenvalues. And because we're assuming that the eigenvalues are distinct, all of these numbers are not 0. Therefore, this is not equal to 0. And so we automatically know that the determinant of this matrix is non-zero. So we can make a guess that the determinant of that more general matrix, of that more general Vandermonde matrix, is exactly the product of the differences of all of the eigenvalues. And therefore is not 0 if they're distinct. And we can prove this by induction. We already know what happens when n equals 1, or when n equals 2, and even n equals 3. And so what we can do is, if we assume that this formula is true for n, and go to n plus 1, then what we want to do is reduce that problem to this one, and show that those numbers factor out, and then we can apply our induction hypothesis and prove that this formula holds more generally. And the way we do that is very similar to this. So I'll put a question mark here, and I'll write what this equals. By doing this first step, which was here, this first step, and subtracting the first row from all of the rows below it, what we end up getting is the determinant of, and here we have a bunch of zeros below the ones. So we have 1, and I'll write 2 rows just so we see more of the pattern. This is a 0, 0, lambda 1, and then this is lambda 2 minus lambda 1, and this is all the way down to lambda n minus lambda 1, all the way up to. And let me write two additional terms here. So this is going to be lambda n minus 2, lambda 1 n minus 1. Now, this is lambda 2 to the n minus 2th power minus lambda 1 to the n minus 2th power. And here we have lambda n minus 1 minus, 2 minus 1. That's a 1. Okay. Now, at this point, we can follow a similar procedure by pulling out a lambda 2 minus lambda 1 from each of the terms, but then we would have to figure out what is lambda 2 to some power minus lambda 1 to that same power divided by lambda 2 minus lambda 1. We could do that and factor it out by using polynomial division, find out what the corresponding factors are, but maybe that's not the best way to do it. Another option, although that method, of course, teaches you a lot about how to do polynomial division in case you haven't seen it before, it's quite nice, but maybe there's another easier way, similar to what we did over here. And what we did here was we took the second last column and we multiplied it by lambda 1, and we took the difference here. We could have also done that in this step. It just might have been it might have looked a little bit more complicated because of the higher powers. But let's try to do that anyway. If we multiply the second last column by lambda 1 from the last column, the power here will be n minus 1, which will match this one. And these two terms will cancel and you'll just get 0. What happens to this term? If you multiply this by lambda 1, so let's write this out. So we have lambda 2 n minus 1 minus lambda 1 to the n minus 1 minus, multiply this whole term by lambda 1. That becomes a plus lambda 1 to the n minus 1, and then what's left over is minus lambda 1, lambda 2 to the n minus 2. These two terms conveniently cancel, and what you're left over with is lambda 2 appears, the highest common factor is lambda 2 to the n minus 2, so we can pull that out. And what's left over after we pull that out is lambda 2 minus lambda 1. And therefore, we can much more easily see that this factors out after we do this subtraction. Now, imagine we've done that for this last column here. Now we have this second last column, which still has all of these complicated terms. But what does this term before it look like? Lambda 1 to the n minus 3, and then it's lambda 2 to the n minus 3 minus lambda 1 to the n minus 3. So you can just see it's of the form n minus j. And if we multiply this by lambda 1 and subtract it, well, these two terms will cancel, and a similar thing will happen here. It's just that the power will now be not lambda 2 to the n minus 2, but lambda 2 to the n minus 3 after we take this difference. And so if we keep going in this direction, taking all of those successive differences, we will be left over with, so this determinant equals the product of lambda j minus lambda 1, and j goes from 2 to n, and we're left over with the determinant of a smaller van der Waals matrix, which looks like 1, 0, 0, and this term is 1, and it's all the way, 1's all the way down. Let me write just the first and last ones. We also have zeros here, up to the last term. Now, what is this term here? It's lambda 2 to the n minus 2 now. all the way down to lambda n to the n minus 2. And if we assume the induction hypothesis, then we know that the determinant here is the product of lambda, let me use a different letter, k and l, so k minus l, where k is greater than, strictly greater than l, and l runs from this time 2 to n, and k. So we end up getting, after all of this work, by using that induction hypothesis, we get that this is this expression right here. And in particular, this says that our determinant is non-zero. So we can compute the inverse of this matrix if we wanted to. Now that we have all of this set up, we can prove our main theorem, which remember said that given any diagonalizable matrix A, there exists, and a function f on its set of eigenvalues, there exists a polynomial q such that q of A equals f of A. And so far, based on the facts that we just proved, we know there exists a polynomial q such that q of lambda I equals f of lambda I for all of the eigenvalues of that matrix. Therefore, if we compute f of d, which was defined to be f of lambda 1, f of lambda n, of our diagonal matrix D, then this is the same exact thing as q of lambda 1, q of lambda n, with 0 everywhere else. By this result, we can find a single polynomial q that satisfies this. But this is exactly the same thing as q of d. Well, why is that? Well, if we write our diagonal matrix D out and we apply the polynomial q to it, right? So let's just see why this is true. If we take our diagonal matrix and then we plug in our polynomial, so we had, what was it? It was A0 times the identity n by n matrix. This is what, if we view q as a polynomial and we plug in the formula for q of d, this is by definition of a matrix applied to a polynomial. Sorry, a polynomial with input a matrix, plus a1d plus a2d squared plus a n minus 1 d to the n minus 1. And we know what this looks like as a matrix. This is the identity. It looks like A0 all along the diagonals and 0 everywhere else. This is A1 times lambda 1 all the way down to A1 times lambda to the n, lambda n. And then here we have plus A2d squared. Now, d squared, since d is the diagonal matrix, is just lambda I squared in each of the diagonal terms. So it's A2 lambda 1 squared all the way down to A2 lambda n squared. And similarly for all of the other terms up until this last one. Then what happens when you add all of these matrices together? Well, you get A0 on the top left term, you get A0 plus A1 lambda 1 plus A2 lambda 1 squared plus dot 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 an1 minus lambda 1 to the n minus 1. That's exactly what q of lambda 1 is. And similarly for all of the other terms. So this justifies why this equality holds. And of course, q of any matrix is defined similarly. So in particular, q of A equals A0 times the identity plus A1 times A plus a2 times a squared, and so on. So now, let's show that f of a equals q of a. Now, f of a, by definition of f of a, is p times f of the diagonal matrix times p inverse, where p is the matrix of eigenvectors corresponding to those eigenvalues, is a matrix of eigenvectors. Now, f of d, by this calculation, is also q applied to d. And so that equation is true by what we just showed. Now, we know what q of d looks like. It looks like this. And we also know what happens when we distribute p throughout. So we get something that looks like a0 p times p inverse plus a1 p d p inverse all the way up to a n minus 1 p d to the n minus 1 p inverse. That's just what that looks like when you distribute p and p inverse on both sides. Now, this is a. And what is this expression? And likewise for all of the terms in between. Well, let's just look at what happens if we set if n is like 3 or something like that, or maybe even 2 is enough. So let's look at this term. P d squared p inverse. So p d squared p inverse also equals p times d times d times p inverse. And because p and p inverse are, well, inverses of each other, we can plug in a p inverse p between these two d's. And this gives us p d p inverse times p d p inverse again. And this is just a, and this is just a, so we get a squared. Therefore, when we actually write out what all of these things equal, we get a0 p inverse plus a1, which is the identity, sorry. This is the identity matrix. And this is a plus a2 a squared plus all the way up to a n minus 1, a to the n minus 1. And this is the definition of q of a. So this shows us that that theorem is true. So this has an interesting corollary. So let A be diagonalizable. And let B be any square matrix of the same size. And suppose that they satisfy the fact that when we multiply them in any order, they're equal to each other. Then, f of a, b equals b f of a for all functions that are defined on the eigenvalues of a. And how do we prove this? Well, because a is diagonalizable, then f of a equals q of a for some polynomial q. And because it's a polynomial, if we replace this expression with q of a times b, so if we have q of a times b, this is a polynomial in a. And each of the terms look like a to the jth power times b. Right? So you have a to the jth power times b. Now, a to the jth power means you write the matrix A j times, and if you have a b on one side, you can use this to move each of those a's one over at a time. You can move them over one at a time. Therefore, a to the jth times b equals b times a to the jth. Therefore, it's immediate that this equals b times q of a. And it immediately solves this problem because q of a equals f of a. And the interesting thing about this is that b can be any matrix whatsoever, and a only has to be diagonalizable for this to be true. So hopefully this is an interesting fact, namely that given any function, at least that's defined on the set of eigenvalues of A. It could be defined on a larger set of the subset of the complex numbers, but at the very least, if it's defined on those eigenvalues, then we can always find a polynomial for which, when we apply that function, which could be completely wild, such as the logarithm or something like that, then there's a polynomial that gives us the same value for that matrix if we apply that polynomial to the matrix versus if we apply the function to that matrix. And a lot of this has to do with the fact that we're working with finite dimensional matrices. One of the interesting things about linear algebra is what happens when your matrices become of infinite order. And then this really becomes a much more subtle issue, and clearly the method that we've used should probably break down. For instance, we're not working with polynomials anymore. And a lot of this is explored, for instance, in functional analysis and spectral theory and the functional calculus for such operators. In these next few videos, we'll learn about affine subspaces, affine combinations, and affine transformations, which are very slight generalizations of linear transformations, as we'll see. So the first definition that we'll need is what an affine combination of vectors is. But to do that, we'll recall what a linear combination is. So a linear combination of vectors v1 through vk in Rn is a combination of the form lambda 1 v1. So we add up all our vectors with some weights, and these weights we'll take to be real numbers. So that's what a linear combination is. And closely related to this, an affine combination of these same vectors is a linear combination. And for short, I may often write just using the summation notation. Oops. Let's call this not k, but j. And this goes from j equals 1 to k. Such that the sum of these coefficients is equal to 1. So it's basically a linear combination, but we have an additional constraint on the coefficients. So for example, when k equals 2, we have two vectors, let's say v1 and v2, then every such affine combination is of the form t v2 plus 1 minus t v1, where t is a real number. And you can look at what this says. Let's say these two vectors are different. Let's say v1 is here and v2 is here. Then at t equals 0, so this is describing the set of all such combinations. And when t equals 0, this gives me v1. So at t equals 0, I'm here. And when t equals 1, I'm at v2. And as you vary t over the set of real numbers, you get all the points along the straight line through v1 and v2. This is very different than the set of all linear combinations of v1 and v2, because if, let's say, the 0 vector were here, then v1 would be this corresponding vector, v2 would be this corresponding vector, and all linear combinations of these two vectors is actually the plane obtained from v1 and v2. That's what the span of these two vectors are. But all affine combinations is just this line. And so just like we can define the span of vectors, we can also define the affine span of vectors. So the affine span of the vectors v1 through vk is, and we denote it by AFF, and it's defined to be the set of all affine combinations. So the set of all lambda j, vj, such that all of the lambda j's are in R, and the sum of them equals 1. So let's look at another example where we take 3 vectors. So let's say v1, v2, v3. And let's just be concrete, and let's say we're in R3 so that we can visualize this a little bit better. So there are several cases that we can take. Just like for linear combinations, for instance, if one of these vectors was a linear combination of the other, then the span of this would be a plane. And if all of them are scalar multiples of each other, then the span is a line. And if they are all the 0 vector, then we just get the 0 vector. And if they're all linearly independent, then we get all of R3. There are many different cases depending on the relationships between v1 through v3. Same thing happens for affine span in the sense that it depends on how these vectors are related. So let's look at 3 possible cases. So case 1, let's say v1, v2, and v3 are not collinear. So this means that all these 3 points don't lie on the same line. So maybe they look something like this. Like for instance, you can take the unit vectors e1, e2, and e3 in R3. Then the affine span of these 3 vectors is equal to the 2-dimensional plane containing these vectors. And it's not so immediately obvious that that's what happens, but let's just think about this. If we take v1 and v2, then it includes the affine span of these 2 vectors, which means we have this line through these 2 vectors is in our affine span. And likewise, the line through v2 and v3 is here. Likewise, the line v1 through v3 is here. And now that we have all of these lines in here, we can also take affine combinations of these points. So we can take, for instance, the affine combination of this point with this point, which gives us this line, this point with this point, which gives us this line. And you can see by taking all such combinations, all such affine combinations of these 3 vectors, we can actually get any point in the plane that contains these 3 points. In case 2, let's imagine that v1, v2, v3 are collinear, but at least 2 are distinct. So in this case, so I'm assuming that at least 2. So either the possibilities are something like they're all different, but they lie on the same line, in which case the affine span of these 3 points is equal to the straight line through those 2 points, those 3 points. Or the other case is the affine span. If 2 of them happen to coincide, then we just have 2 points. But I'm assuming that they're collinear and at least 2 are distinct, so we also get the straight line through those 2 points. And the final case, case 3, is when all those vectors are exactly the same vector. And when this happens, we only have a single point. And all affine combinations of a single point is just that point itself. So these are some of the basic constructions that you can do with vectors. Besides just taking linear combinations, you can also take affine combinations. There's yet another type, which we won't discuss, is if you require that the sum of these coefficients adds up to 1, but they're also not just real numbers, but they're strictly non-negative. So they have to be at least 0. And that's called a convex combination, which is a closer related idea. And in the case of these 3 vectors, for instance, it would be the triangle whose 3 vertices are those 3 vectors that we had here. And in this case, if we took convex combinations, it would be the interval between these 2 farthest endpoints. And in this case, we would have the same situation as we had here, where we would just get a single point. A common question that we ask, given a set of vectors, is if we have another vector, when is that vector in the span of those vectors? And this shows up, for instance, if we solve a homogeneous linear system, and we have a bunch of solutions that we know are actually solving that system, but let's say we don't know exactly what that system is. We just know we have this collection of solutions. And if somebody hands us another vector, then we can ask, is that vector definitely a solution of the system that we have? And in this case, since we don't know the system, we can't plug in that vector to check. Instead, what we have to do is check if that vector is in the span of the vectors that we have already. If that vector is in the span of the vectors that we already have, then that vector is definitely a solution. But it doesn't tell us that if it's not in the span of those vectors, then it's not a solution, because we might not have had a set of vectors that span the solution set. But at the very least, it gives us a criteria for guaranteeing that if that vector is in the span, it's definitely a solution. And likewise, you can ask, well, if I have a bunch of vectors that I happen to know solve an inhomogeneous equation, and somebody hands me another vector, is there a similar criteria? And there is, and that involves the notion of affine span, which we talked about in the last video. So the question that we could ask is, given vectors v1 through vk, and another vector, u, in Rn, when is u in the affine span of these vectors v1 through vk? Now, in order for us to solve this problem, then we have to be able to write u as a linear combination of v1 through vk, right? But because it's an affine combination, we have an additional constraint on what these coefficients could be. And that constraint is that lambda 1 plus lambda k equals 1, which is also a linear system in the unknowns lambda 1 through lambda k. And therefore, if we want to solve this system, this question is equivalent to the following one, which is the augmented matrix where we take our vectors v1 through vk augment it with the vector u, but in addition, augment this further by one additional row, stating that 1 equals, so now this is the number 1, equals 1 dot 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 1. Let me write this 1 so it's clear. So this vector is just denoting the fact that it could have several entries. So we have an additional row in our augmented matrix. And the question is this consistent? So this is actually how we would solve such a problem. And how does it show up in solving inhomogeneous systems? We'll get to that after we talk about what an affine subspace is and the fact that the solution set of an inhomogeneous system is an affine subspace. So for this, let's just briefly recall a vector subspace. I'll put vector usually in parentheses, but a vector subspace of Rn is first of all a subset. Let's call it V, such that 3 conditions hold. Now there are many equivalent ways to define such a thing, but this one seems pretty concise and simple. And the first condition is that the 0 vector is in V. The second condition is that if you take a vector in V and you scale it by any number, then that scalar multiple is also in V. So lambda V is in V, provided that the vector V was in V to begin with, and lambda is a real number. And 3, the third condition is that if I take any 2 vectors in V, then the sum of them are in V. So let's write U plus V is in V for all pairs U and V that are already in V. And this is what a vector subspace is. Now this definition of a vector space is a little bit algebraic. It's telling us when certain vectors are in V, and we can have a little bit more of a geometric interpretation of what a vector subspace is by using affine combinations. So equivalently, V satisfies, which means that if V satisfies the following conditions I'm about to write, then it satisfies this one, and conversely, let's call it instead of I and 2, so let's use I because the first one's the same. The 0 vector is in V. And the second condition, which is sort of a combination of these two, is that Tu plus 1 minus TV is in V for all T in real numbers and for all U and V in V. Now this is exactly a linear combination of the vectors U and V. So if I take 2 vectors U and V inside of V, then this affine combination is describing the set of all points along the straight line through those 2 vectors. So this is saying that a subspace can also be described as a plane that contains the 0 vector. And plane could mean hyperplane. And this is because we always have the straight line through any 2 points in our subspace. Now, the fact that we've written it this way allows us to define an affine subspace in a much more closely related fashion to this definition, because for an affine subspace, we'll only be able to combine vectors in an affine way. So we define an affine subspace is a subset A of Rn such that, and now we drop this first condition. So all we require is that affine combinations of 2 vectors are always inside. So Tu plus 1 minus Tv are in V for all same conditions as here. And you can ask, well, maybe an affine subspace should be, if I take any collection of points inside of it, then the affine span of those points is inside of V. And that actually follows from this condition and the usual properties of scalar multiplication in vector spaces and how you add them. So the main example that we want to illustrate is the solution set of any linear system ax equals b. This is just notation for a linear system where b is a vector in Rm and A is an m by n matrix. So the solution set of this is an affine subspace of Rn. Now, the solution set of an inhomogeneous system is not a vector subspace because in general 0 is not a solution. In fact, when 0 is a solution, then it exactly is a subspace. And when 0 is not a solution, we get this more general notion of an affine subspace. And it's a fact that affine subspaces are translates of vector subspaces. And what do I mean by that? A is an affine subspace if and only if there exists a vector v in Rn such that if I take this affine subspace A and subtract v from it, now what this means is the set of all vectors of the form u minus v, where u is in A, if this subset of Rn is a subspace, in this sense, is a vector subspace. In fact, we can use any vector inside of A to translate it to the origin. So in fact, v will be a vector in A. In fact, any vector in A will make this a vector subspace. So the picture for this is actually really nice. I guess I shouldn't have called it A because I called this linear system A. That may be potentially confusing. So maybe let's call this script A. So let me use a script A here. And fortunately, the letter A was only used in this one example. But let me write it like this here so it's the same. So there's no conflicting notation. OK, so here's our affine subspace A. And if we take any vector in here, let's call it u. No, let's call it v. So v points from 0 up to where that vector is. And if we take this vector and we subtract it, then v minus itself will be 0. So I know that this plane is going to contain the 0 vector. And so here we have A minus v. And no matter which v we picked, right, if we picked another one, let's say we picked this vector right here. Let's call this one u. Then if we translate that, u minus itself is 0, so we also get this plane back as well. And so a good application of this sort of mathematical object is if the vector xp, p for particular, is a solution to ax equals b for some linear system like in the previous example, then the solution set, meaning all the solutions of ax equals b, is as we know, the particular solution plus the homogeneous solution set. So it's the set of all sums of particular solutions with homogeneous solutions. So AXP solves the system this, and AX homogeneous solves the associated homogeneous system. So if A represented the solution set of an inhomogeneous system, and A minus V represents the solution set of a homogeneous system, then all we have to do is pick one of these solutions, and then all of these solutions, and then take that solution and translate it by that vector, which was a particular solution of the inhomogeneous system. Just as we can define linear transformations, which are functions that take linear combinations to linear combinations, we can also define affine transformations. And the idea is that they take affine combinations to affine combinations, which translates geometrically to it takes lines or hyperplanes to other lines and hyperplanes as well. So the definition of an affine transformation is exactly that. An affine transformation, in this case from Rn to Rm, is a function, first and foremost, and I will write my arrows as usual from right to left. So it's a function, let's call it S, such that S of lambda u plus 1 minus lambda v is equal to lambda s of u plus 1 minus lambda s of v for all u and v in Rn, and for all lambda in R. And it's a consequence of this definition that if we take any affine combination of vectors, then S of that affine combination is going to be the affine combination of S applied to each of those vectors. This is a little less obvious than it is if you take linear transformations and you show that it follows from the assumptions of a linear transformation that it takes linear combinations to linear combinations. And the reason it's a little bit slightly more challenging is that if you apply this in a binary fashion, right, if you take two vectors u and v, so you think of this as a function from, let's say, r cross r to the n cross r to the n, to r to the m, then in order to apply this here, you have to put parentheses in the appropriate place. But in order to have an affine combination with the appropriate parentheses, you have to be a little bit careful about what your resulting coefficients are. And it's not so easy to see how to do that, but it can be done. And here's the example that I really like to think of when comparing linear transformations to affine transformations and things you might have seen from a while back. Not in my lectures, but in your early learnings of math, perhaps. So if we take the usual equation of the form y of x equals mx plus b, where m and b are both real numbers, and x is a variable, and y is the function of x, then this is an affine transformation from R to R, because it takes a real number R, x, and it gives us another real number. And it's linear if and only if b equals 0. Linear in the sense of being a linear transformation. So this will help you, perhaps, relate the difference between an affine transformation and a linear one. And we'll later talk about a theorem that relates the two exactly together In fact, we'll state that theorem now. So the theorem says the following are equivalent for a function. Now we're just describing a function. And these conditions are that S is affine, is an affine transformation. So I'm not assuming any linearity. This is just an ordinary function. So S is affine. If I take the function S and subtract S of 0 from it, so if I take S minus S of 0, now this is a function in the sense that if I take any x, the function associated to this is defined by S of x minus S of 0. So this is also a function from Rn to Rm. If this is linear, and C, there exists an m by n matrix, M, and a vector B in Rm such that S of x equals mx plus b. And the reason I mention this example is precisely because of this theorem, because it allows us to relate affine transformations to transformations that we may have seen a long time ago. And I personally think it's instructive to prove this theorem to get a feeling for how affine combinations work. So let's actually prove it. And we'll prove this by proving A implies B implies C implies A. So for the first part of this proof, we're going to define, I don't want to keep writing S minus S of 0, so we're going to define L to be this function S minus S of 0. And the goal is to prove that this function is linear. So we have to check the associated conditions for linearity. And before we do that, let's just establish that if we apply 0 to L, if we apply L to 0, then we get exactly 0 because this is S of 0 minus S of 0. So it definitely preserves 0. And we know that this doesn't give us a sufficient condition for linearity, but it's definitely necessary. So second, if we take a coefficient lambda, any real number lambda, and if we take a vector u that's inside of Rn, then by this definition, this is S of lambda u minus S of 0. And this is an interesting combination of lambda u and 0. This also equals S of lambda u plus 1 minus lambda of the 0 vector, right? The 0 vector is in the domain of S, and so I can multiply it by any number and I still get 0. And now the interesting thing about this is that this is an affine combination of the vectors u and 0. So that's what this term is, and this just comes along for the ride. Because S is affine, I can take these coefficients out. And this is also an affine combination of itself. So I can write minus lambda S of 0 minus 1 minus lambda S of 0. And so what do we have? We have lambda of S of u in parentheses minus S of 0, which is exactly L of u. And these two terms cancel. So we're left over with lambda L of u when we're done with this calculation. So it's linear in this, it's the first condition of linearity is proven. And then the second condition is if we take a linear combination. This also has to go to a linear combination as well. So let's just use the definition. This is S of u plus v minus S of 0. And now let's draw a picture here because this is going to help. Let's say we have the vector u here and the vector v here. And this is the 0 vector. Now the vector u plus v is somewhere here. Now, can we express u plus v as some convenient affine combination of vectors for which we know what S does to those vectors? Well, if we extend u, so we take combinations of u and combinations of v, then u plus v can be written as an affine combination of some multiple of u and some multiple of v. In fact, it can be written like that in many ways. All I have to do is pick any point here and draw the straight line through this point and u plus v, and then find out what that vector is. Or we can take a simple shortcut and just notice that if we multiply this by 2, this by 2, then those 2 points, 2u and 2v, are on the same line are on the line that goes through u plus v. And how do I know that? Well, if I take half of this and half of this, I get exactly this. And half is an affine combination. So this equals S of 1/2 2u plus 1/2 2v minus S of 0. And because this is an affine combination, we have 1/2 S of 2u plus 1/2 S of 2v. And now we can also subtract half of S of 0 here minus 1/2 S of 0 again. And now 1/2 is a common factor here. So this gives us 1/2 L of 2u plus 1/2 L of 2v. But by the thing we just proved, we know that we can pull out scalars from L. So this gives us L of u plus L of v. And this together proves the linearity. So this is the proof that A implies B. That if we have an affine transformation, we subtract by what it applies to when you plug in 0, then we get a linear transformation. Now the rest of the proof is actually not bad afterwards, because for B implies C, if we have a linear transformation, we already know we have a matrix corresponding to it. So because L is linear, we get an m by m matrix such that L of x equals m of x equals m times x for all x in the domain of S, which is Rn. So set B to be equal to S of 0. And when we set that to be that, then since L is S minus S of 0, then we take S equals L plus S0, which is B. Then we get the equation of the form S of x equals mx plus b. So that's how B implies C. And then if we have C to imply A, this is it's very similar to these kinds of calculations of taking affine combinations. If we take S of, like let's say, lambda u plus 1 minus lambda v, plug that in here, we know m acts in a linear way. This is a matrix. We apply matrix multiplication, distributivity, associativity of all these properties of addition of vectors and scalar multiplication of vectors in Rm. And we get that S is affine from this assumption. So these three conditions are equivalent for any function from Rn to Rm that characterize what it means for a transformation to be affine. As we know, functions can be composed provided that the domains and codomains of these functions match up. Similarly, affine transformations compose, and the composition is affine in an analogous way to how linear combinations are composed, and the resulting composition is also linear. So we have a fact, and this fact is that the composition of two affine transformations, S and T, is also affine. And because it's affine, and we know that each of these transformations can be written in the form of mx plus b for some appropriate matrices and appropriate vectors b, we can ask, what is the resulting matrix for, what are the resulting matrices and vectors for the composition of two affine transformations? So let's write S of x as mx plus b and t of y as nx plus ny plus c. And let's just be careful about composing these. So if we take the composition, S composed with t, and we apply a vector y, then this by definition is S applied to t of y, and we know that t is of this form. So we get ny plus c. And this equals m times the input of this function, which is ny plus c, plus the associated b, oh, this should be a plus, from the transformation S. And if you distribute this all out, we get mn times y plus mc plus b. So the associated matrix that we get is actually just the multiplication of the matrices that we started with, and the associated vector b is some interesting combination of the original vectors b and c, but also with the matrix M. And in particular, if S from same setup, Rn to Rm, is invertible, and we wrote our decomposition like this, then we could ask, what are the matrices and vectors associated to the inverse of this matrix? And that is exactly, so S inverse, let's write of y, just because we're changing the codomains with the domains. We get the inverse of m plus, well, rather minus, m inverse of the vector b. And why does this work? Well, if you just take S, for instance, and you apply it to this result, we know what this combination looks like. We get m applied to this term, which gives us just y back, m applied to this term, which gives us negative b, but we have a plus b, and those two cancel. So just like the composition of linear transformations need not commute, similarly, the composition of affine transformations need not commute. So let's look at an example. And a common affine transformation is leave everything alone, just translate by some vector. So let's just keep things very simple, and let's assume that we translate by the vector 1, 0. So we shift everything along the x-axis in R2. So we shift everything along the x-axis. So let's say the vector, let's draw a smiley face here. This smiley face transforms under this transformation. Let's say smiley face is contained in the unit box, so I'll have to make this a little bit bigger. And it gets translated along the x-axis in the positive direction. So let's call this transformation T. Another transformation that we can look at, let's call this one S, is rotation by 90 degrees. So when we rotate, the face looks something like this. And then we can ask what happens when we apply S and T in that order, or if we apply T then S. And what are the matrices and vectors associated to these transformations? Let's actually answer that question first. So T of any vector x equals, well, let's just translate. So it says leave everything in the plane alone, so that's the matrix corresponding to the identity, and shift by the unit vector in the x direction. So I call that E1. So remember, E1 equals the vector 1, 0. And S of x is the transformation that rotates by 90 degrees. So I'm going to write that in matrix form, because rotation by 90 degrees is 0, negative 1, 1, 0 applied to the vector x. And the b here is 0 because this is actually a linear transformation. So what happens when we compose these in different orders? So let's just think about this. Imagine you translate first and then you rotate. This rotation is occurring about the origin. So when we apply t first and then we apply s again, we're rotating this picture by 90 degrees with respect to this origin. So this face is actually going to be further out than it would have been if we applied the rotation initially and then translated. You can already see the big difference between these two pictures. So if we apply first t and s applied to this picture, let's start with our initial configuration. Then what happens after you apply this? Well, first you rotate and then you translate. So this translates everything to something that looks like this. But if instead we applied s after t to the same initial configuration, well, first we would translate and then we would rotate by 90 degrees. That would look much, much different. So if I were to draw this as a unit grid, that face would now be in this box, rotated by 90 degrees. So it would look something like that. So now let's just check the math out to make sure that this is consistent with these geometric interpretations. So if we apply t after s to any vector x, what do we get? Well, t says first translate, then rotate. So we end up translating by x, then rotating, because we do matrix multiplication, and the resulting vector b is just E1. So we get rotation applied to x plus E1, which is exactly what we expected from our picture here. If we did it in the other order, well, in that case, first we translate, and then we rotate. And when we rotate, we not only apply the rotation to our initial vector x, but we also apply the rotation to the vector E1. And E1 gets rotated by a 90-degree rotation to the vector E2. So in this case, we get this instead. So, and this is consistent with this picture, because if we rotate first, our face ends up somewhere here, like in this picture. And then how do we get from this picture to this one? We translate up by a unit vector, by the unit vector E2. The next few videos are going to be a sort of combination of probability theory and matrix algebra. And we'll start by talking about finite sets and stochastic matrices, or what I call stochastic maps. And we'll try to get through a lot of interesting topics. So first, I just want to make sure that we have all these definitions at hand. And the first one that I want to make is a probability measure. And for simplicity, we will be working with finite sets all the time. So a probability measure on x, where here x is a finite set, is a function that takes every element of x, and it gives me a number, and that number is between 0 and 1, and the sum of these numbers, when I sum over all elements in x, and let me just set notation that when I apply this probability measure to x, instead of writing p of x, I will write p subscript x, so such that the sum of these numbers equals 1. And a stochastic map is something very similar to this. And let me even set some more notation. The set of all probability measures on X is denoted by Px. So a stochastic map from X to Y, so another finite set, is a function from X to probability measures on Y. Let's call that F. And we're going to introduce a convenient notation for such stochastic maps. So first let's explain a convenient notation for how to write F. So if we take an element X and we apply it, we'll get a probability measure on Y. For now, let's just call this f of x. Because this is a probability measure, it takes an element y in y and gives me a number between 0 and 1. So this takes an element y and maps it to f of x of y. Now it's a little bit annoying to write something like this and potentially confusing. So instead of writing this, we will write f subscript yx. And the reason we write the y on the left is because we will end up in y and x on the right because we started in x. We'll see why this is convenient in a moment when we talk about composition of stochastic maps. And we'll also introduce graphical notation for this. Instead of writing a map from x to py, we will replace this by a map from x to y, but we'll use slightly different notation for our arrows, and we'll make them squiggly arrows like this. And the reason we want to do this is because there's a very nice example of a stochastic map if we have a function. So if x to y is a function, this actually gives us a natural stochastic map. And just for this example, we'll call it delta f. Oops, these should be squiggly arrows now. So delta f to y, which sends an element x to a probability measure on y. And what should that probability measure be? Well, if I take, let's call this delta f for now. If I take an element in y and I plug in our initial element x, so again, we're using this notation here, then this is defined to be the Kronecker delta. So if we take the element x, apply f to it, we know what that is because we have a function already. And then we plug in y. So visually, how do I think of something like this? Well, a stochastic map is telling us if we start off in x, let me draw the arrows backwards for a moment, then it takes an element in x and it spreads that element out over y by giving us a probability distribution on y. But if we already have a function, then we know where that element x goes. It goes to a specific element which we call f of x. And therefore, it does give us a probability distribution. And that probability distribution is 1 when we evaluate it at f of x and 0 everywhere else. So I think of this as a deterministic process in some sense because we know, given an input, we know exactly what the output will be with 100% probability. So we notice that there's this close relationship between functions and stochastic maps. In fact, functions are special kinds of stochastic maps. And instead of writing delta f all the time, we'll simply write xf, and we will think of this as a stochastic map, but we'll write it as a straight arrow. Another example, there is a one-to-one correspondence between stochastic maps from a single element set into another finite set X. So this is going to be my notation for a set containing a single element, which I'm just calling a bullet, and probability measures on X. Why is that? Well, if I have a stochastic map, I apply an element of it, I apply it to an element of the domain, and that gives me a probability measure on X. But this only has one element, so I only get one probability measure. So in general, a stochastic map is, you can think of it as a family of probability measures indexed by the domain of that stochastic map. Stochastic maps define conditional probabilities. Or at least some kind of restricted notion of conditional probabilities. And the reason is because Fyx, you can think of this as the probability of y occurring given that x has occurred. And you can, if you have a definition of conditional probability and you are looking at single element events, then this definition coincides with the one you're thinking of for finite sets, and again, single element events. But if you're not, then we're going to think of this as our notion of a conditional probability. So for being very concrete, let's take X to be the set whose elements are, so pick your favorite supermarket, and let's say there's a good sale at that supermarket. And let me think of that as one element of this set X. And the other element is going to be a not great sale or a not good sale at that same supermarket. So two elements, and let Y be the elements that state whether I go to the supermarket this week or you go or whatever, or I don't go. So I go to the supermarket, let's say this week or something like that, or I don't go. And let's say if there's a good sale, let's say the probability, right, because I might have a lot of food stocked in my pantry, I may or may not go to the grocery store this week, but if there's a good sale, maybe there's a good chance that I'll go. Let's say there's a 90% chance that I'll go. And if there isn't a good sale, well, it might be that I still need to get food, so there's still going to be some chance that I go, but perhaps it'll be less. I'll be less enticed to go to that supermarket this week. Let's just say that there's a 60% chance I'll go. And with this information, we can define a stochastic map from X to Y. So this actually defines a stochastic map, and we'll come back to this in several examples that we'll look at later on, because it's a nice simple example. And the reason you can figure out what the rest of this is just by using probabilities, because if there is a good sale, the chance that I go is 90%, then there's a 10% chance I won't go, and conversely, if there isn't a good sale, then there's a 40% chance I don't go. So that defines a stochastic map. Just like with functions, we can compose stochastic maps as well, but this is going to have a really nice picture, so I rather give that its own video, and we'll talk about compositions in a moment. All right, so if we have two finite sets, rather three finite sets, x, y, and z, and a stochastic maps between them in such a way so that the codomain of f lines up with the domain of g. And I really mean source and target here, because again, if I really think of x as a function, it's a map from x to probability measures on y, but the domain of G is not probability measures on y, it's y itself. So it's really better to think of this a little bit categorically, where I'm thinking of the target of f and the source of G. So given this, given stochastic maps, we can define a composition of these two. And before I write down the formula, let's think about how we would do this. So if here's x, here's y, here's z, what we want to define is a notion of composition, which is determined by if you give me an element in x and you give me an element in z, I want to know, given x, what is the probability that z occurs? And there's an intermediary y here. So the way that you get that is, well, I look at all the elements of y, and I look at, given x, what is the probability of that element y occurring? Let's say that this is the element y. Then this is fyx. So given x, the probability that y occurs, and going from y, what's the probability that z occurs? That also has a probability, which is gzy. And so the probability of given x, the probability of z given x, is taking all of these probabilities by varying y and multiplying the corresponding ones when they match up, and then adding them all. So this is defined to be the sum over all elements in y with their respective probabilities, g, zy, f, y, x. So this is what the composition of stochastic maps is. And now you can see why I chose this notation earlier of writing our subscripts in this particular order, because if I think of these as matrices indexed by the elements of these sets that we have, then this ends up just being matrix multiplication. So sometimes these are also called stochastic matrices, but I'm going to stick to calling them stochastic maps. So let's look at some interesting special cases of this definition. So first, let's look at the special case where x is replaced by a single element set, y is a set x, and g is a function, not just a stochastic map. So let's take this special example. So let's take y, a function f, and a probability measure on x. So first of all, what does a probability measure on x look like? Well, if I think of x as a set, so let's draw some of the elements of x here. Let's say here we have 9 elements. A probability measure sort of gives me a size to each of these elements. So I can think of these as water droplets, each with a specific size. Namely the volume. So this is sort of what a generic x looks like with a probability measure on it. And the sum of the volumes of these water droplets is equal to 1. Now if I have a function f from y to x, then the composite here gives me a probability measure on y. What is that probability measure? Well, if I just use the definition, p followed by f, and I evaluate it at y, this is equal to, just straight from the definition, we know that this is the sum over all elements in x of the function on the left, which is f, but f is a function, so we know that it corresponds to the direct delta, the Kronecker delta, f, y, f of x with the probability measure px. Now if I substitute what this looks like, this says this only gives me a non-zero contribution if f of x equals y. In other words, if y is in the image of f of x, is in the image of f, and it comes from some x. So if we look at the inverse image of y, that's going to give me a bunch of elements, and that's the only case where this gives me a non-zero contribution. And what that means is that this breaks down into the sum of all elements x in the inverse image of y. So here we have the sum of all the px's that are in the inverse image of an element y. So let's look at this element y here. The inverse image of this under a map F. So let's imagine that F identifies all the elements that are in the vertical direction. So, right, because a function f might not be one-to-one, so it might identify some of the elements, and that's why I've drawn it this way. It takes these four elements and gives me the single output y. And these two elements gives me another output. And what this condition says is that the probability here is the sum of these probabilities. In other words, the volume of this water droplet is the sum of the volumes of those water droplets. Likewise here, in order to make the volume somewhat geometrically similar to these, this would be the resulting volume after we apply this function f, and here maybe it's this big. So this gives us a nice picture of what compositions like this look like. It essentially says that we take these water droplets and then we combine them, and when you combine the associated water droplets, their volumes add. As another example, let's go back to our previous situation. In fact, let me write that example here because it's a little bit, it can fit here. So in this case, we had that set x to be there's a good sale at the supermarket this week and there's not a good sale. And the set y is I go to the supermarket or I don't. Now, what if we happen to know the statistics or the probabilities of whether there is a good sale or not at the specific supermarket given that specific week? So you compile all of your data over the course of a year, for instance, and you just ignore the seasons, you ignore the months, you just look at when is there a good sale for whatever definition of good you might have for you. And let's just say that the probability of a good sale is maybe only 30%. So roughly 30% of the time there's a good sale on a given week. And therefore the probability of a not so good sale is 70%. And so you might ask, what is the probability that I go to the supermarket ? So that's the end of the statement. So all we know is that if there's a good sale, we already know what those probabilities are. I think they were 90% and if there is a good sale, and 60% if there isn't a good sale, because I still need to eat. And if we happen to know the probability that there's a good sale, and therefore the probability of there being a bad sale, or not good rather, is 70%, then you could still ask, what is the probability that I actually end up going? And that's where this composition comes in, where instead of having an f like this, we instead have our f from our previous example, but we also know the probabilities of whether or not there's a good sale. So it's a slight generalization of this example. And therefore, the probability that I go to the supermarket is equal to, and in this case, I'm going to take the probability that there is a good sale times the probability that I go given that there's a good sale, plus, so let me actually write that one down. So that's 90% times 30%. The probability that there's a good sale times the probability that I go, plus the probability that there isn't a good sale, but I still go. And the probability that I go given that there isn't a good sale is 60%, and the probability that there is not a good sale is 70%, and the resulting probability that I go is 69%. So given those statistics, we still know that if I just chose an arbitrary week in the year, there's a 69% chance that I'll go to the supermarket that week. So now let's look at another example. And this example, again, we'll come back to this perhaps a few more times. So now let's look at another example. This one may seem a little bit abstract, but it's a very useful one anyway. So let's take the diagonal map from x to x cross x. What this does is it takes an element x. So far we've talked about stochastic maps and how to compose them, and how to view ordinary functions as specific examples of stochastic maps. What we'll do now is describe how to take the product of two stochastic maps in a way that generalizes the usual notion of the Cartesian product of two functions. So given stochastic maps f and g, we can form their product and it's another stochastic map that essentially takes the product of these two of the associated probabilities pointwise. So it's determined by the formula f cross g. Now remember what our notation is. For each element in the domain, we get a probability distribution on the codomain, and that probability distribution is determined by what it does to points, because we're working with finite sets. So that probability distribution is determined by the value of our initial input with our output. And it's just the product of the associated probabilities from f and g. And let's just check that, make sure that this coincides with our usual definition of Cartesian product when we specify that these stochastic maps correspond to functions. So if f and g are functions, or how I think of them as being deterministic, then this product is given by, well, we know what happens when these are functions. Then we use the Kronecker delta, and this is x prime f of x, while this is delta y prime g of y. And this is nothing but, it's the same exact thing as requiring that x prime coincides with f of x simultaneously as y prime coincides with g of y. And this is the usual way we think about the Cartesian product, because it says, what is the value of f cross g at xy? Well, it's f of x comma g of y. And this is exactly what encompasses that idea. And all of the structure that we've defined so far, the idea of the stochastic map, its definition, how it composes, the fact that functions are special cases, in particular the identity function is a special kind of stochastic map. It turns out that composition is associative. The identity is an identity for the composition for any finite set. And this Cartesian product, it also satisfies a type of associativity condition. And together, all of these data give the collection of finite sets with stochastic maps and this associated product. It gives it the structure of a symmetric monoidal category. But there's another thing that we haven't yet discussed, which is a notion of almost everywhere equivalence, or in other words, an almost surely notion of equivalence. And this essentially takes care of when probabilities happen to vanish. And when such a thing happens, we can have a notion of equivalence between functions when their probabilities are equal versus when they're not, when they're zero. And so we get a very natural definition of what it means for two stochastic maps, very similar to the way we define almost everywhere equivalence for functions. So given two stochastic maps, so I'm using different notation than what's up here. So given two stochastic maps and a probability measure on X, we say that F is P almost everywhere equivalent to G if and only if. And the way we define equivalence is that these stochastic maps agree everywhere outside a set of measure 0, so outside of events that have probability 0. So the way we write that is if and only if the probability of the set of points on the domains of these corresponding stochastic maps where these two stochastic maps differ is equal to 0. Now, what does this inequality mean? Now, f of x and g of x are both probability measures on y. So when I write that they're not equal, that means f subscript yx is not equal to g subscript yx for some y. So this is a very intuitive notion of almost everywhere equivalence. There's another sort of diagrammatic way that you can encompass these definitions as well. So I'll write this as a theorem, but we'll use this idea later on. So it turns out that given f, g, and p as in this definition, f is almost everywhere equivalent to g, so this is the notation that we'll use, if and only if the diagram, now this is going to be a little bit of an interesting diagram. So we're going to produce our probability on x. We're going to duplicate x using the map that we introduced earlier. And on each of these two factors, we will apply our associated maps f and g on their corresponding terms. So in this case, we'll have the identity on x here cross f, and here it's the identity on x cross g, where this product is the one that we just defined. So if and only if this diagram commutes. So first of all, this is a very interesting statement. It tells us that this notion of almost everywhere equivalence can be encompassed in some diagrammatic form. And secondly, if we ever discuss these in these videos, we'll find out that this is very closely related to a notion of almost everywhere equivalence in a non-commutative setting where we replace our finite sets and stochastic maps with certain kinds of C-star algebras and completely positive unital maps. And these sorts of objects are relevant in quantum information theory. Okay, so before we prove this, we'll have a little bit of a lemma just to make the calculation a little bit easier. And that lemma is the composition of two maps, of two stochastic maps that are of this form. So if I have a map phi from u into v and a map psi from u into v, and I precompose with this diagonal map, then this composition is given by the formula. So we take phi cross psi, compose with this diagonal, and how do we evaluate this? Well, the domain has a u and the codomain has a v and a w, so we can evaluate it v comma w and u. And the claim is that this is given by taking just the product of these where two of the points happen to match up. So this is phi VU, psi WU for all VU and W. So the proof of this is pretty easy once we have all of our definitions in place. And the left-hand side of this expression, by definition of the composition and by using the definition of the product, is equal to a sum. And what's our intermediary step? It's the sum over U cross U. And U cross U, therefore, we have to sum over two elements. We're already using the letter U, so we're going to have to introduce U prime and U double prime, for instance. So it's going to be U prime, U double prime, both elements in U. And the product here is going to be phi V U prime, psi W U double prime, because that's the second coordinate. And this is, as we recall, the Kronecker delta twice, using the coordinate U and U double prime and U prime. So it's U prime U, delta, U double prime U. So this gives us two delta functions, and we have a summation over those. And as a result, these two letters coincide. So this is exactly the right-hand side. Quick and simple proof. So this is the proof of the lemma. And then the proof of the theorem. We'll now talk about Bayes' theorem. And first we'll state the theorem. Given a probability distribution on X and a conditional probability from X to Y, call it F, so a stochastic map, there exists another map going in the opposite direction, let's call it G, such that the diagram, now the diagram looks a little bit complicated, but it's not too bad. When we write out the equation, we'll see exactly what it means. So here we'll have P, and here, notice, we can compose P with F to get another probability distribution on Y, and we'll call that Q. So we have our probability distribution on X, on 1 on Y. We duplicate X. We duplicate Y. This almost reminds me of the definition of AE equivalence. X cross Y. And here, we will apply the only maps we can. And to go from X to Y, we apply F. And to go from Y to X, we apply G. So the statement is that this diagram commutes. And furthermore, for any other stochastic map that also goes in the opposite direction, let's call it G prime, satisfying this, then these two maps are almost everywhere equivalent, and in the sense of our probability Q. So this is the formal statement of Bayes' theorem. And if you've seen Bayes' theorem in a different context, this may seem totally strange, but let's just see exactly what it says when we look at the composition of all of these arrows. We've actually computed expressions just like this. If you remember this left-hand side, when we were doing the notion of almost everywhere equivalence in that diagrammatic perspective, we computed something, I think it may have been exactly this expression, actually. So commutativity says that Fyx times Px equals, and if we did that same calculation, but on the right-hand side of this diagram, it looks almost the same. It's just that the g is on the other side. Nevertheless, we still get g xy qy. And this holds for all xy. of course, x is in x and y is in y. Now, let's introduce some notation to see how to understand this. Let's define P of y given x, so this is the probability of y given x, to be exactly fyx. That's exactly what f means. F is a stochastic map. It says it's not corresponding to a function. It says if you give me x, I will give you y with some probability. The probability is exactly fyx. So that's exactly what this conditional probability is. And the probability of x is just little px. The conditional probability of x given y, now this is going in the opposite direction. It says if you give me y, what's the probability of x occurring? That's exactly gxy. And finally, the probability of y occurring is qy. And so if we write down these expressions, commutativity of this diagram says nothing but the probability of x given y times the probability of x is equal to the probability of x given y times the probability of y, which is perhaps a slightly more familiar form of Bayes' theorem, at least when your events are singleton sets. And with the appropriate definitions, you can also extend this, or you can look at what this diagram means because these are corresponding to probability measures, and you can also define a notion of conditional probability where you replace this point with a subset, and you can use the probabilities on your corresponding spaces to make sense of what this means when x is replaced by some event A, perhaps, and y is replaced by some event B. Nevertheless, the same equation still follows from commutativity of this diagram. So let's look at our earlier example just to see what this is saying and how to interpret it in sort of a real-life situation. So if you remember, we had x and y, two sets with each of which contains two elements. And x corresponded to the set where there's a good sale, and the other element was not a great sale, not good sale. And y is the set of elements, the set containing the elements I go to the store, the grocery store, or I don't go. And we also had probabilities on each of these spaces, and we also knew the probabilities that if there's a good sale, how likely am I to go, right? That was 90%. So 90% if good, I go with 90% probability, and if not good, then I still go, but with 60% chance. And likewise, the other probabilities are given by the fact that it's 1 minus this, 1 minus this. And we also know the probability of there actually being a good sale. So we know what P of good sale is, and the probability is 30%, and the probability of a not good sale is, therefore, 70%. So we have all of this information. Now, imagine you're in that store this particular week, and you happen to see me there. So in that case, you happen to know I'm already at the store. Then you can ask, what is the probability that there's a good sale this week, given the information that you see and knowing this information as well? So initially, you also know the statistics that says if I look over the entire year, the probability that there's a good sale is 30%. But you also know that I'm more likely to go to the store if there is a sale. So if you see me, then there might be a better chance that there's a sale this week. And how do you figure that out? Well, if we look at this expression and we compare these two sides, then we can say that f corresponds to the if there's a good sale versus if there's not a good sale, how likely am I to go or not, as fyx. And the probability that there's a good sale is px. And if we wanted to know, so let's say g is on the other side, so g of x given y, so this says if you see me at the store. So here this element y is I'm at the store. And x is there's a good sale. So if you see me at the store, what's the probability of there being a good sale? And we divide that by QY, which we've already determined last time. So QY was the probability that I went to the store. And we know that that equals the sum of the product of the probability of if there's a good sale, I go, and if there's not a good sale, I go, multiplied by the corresponding probabilities corresponding to here. And we found that to be 69%. So in this case, this equals 90%, 30% divided by 69%. And when you write out what this equals, it's roughly, approximately equal to 39%. So you've updated your hypothesis based on what you see. And this is known as Bayesian inference or inversion. And in fact, the map G constructed here, a G from Bayes' theorem, is called a Bayesian inverse of f. And it would be a little bit inappropriate to say that it only depends on f, because it also depends on your prior probability distribution p. So this is an interesting reformulation of Bayes' theorem that seems to be totally in the language of category theory, and it therefore makes it amenable to a wide range of techniques that could be used to analyze and understand it, and perhaps even generalize this idea to other contexts.